just to kind of get started, I believe the initial part is something that all of you understand why we do statistics, what are the different types of statistics, what are the different parts of statistics involved. I believe that part is something that most of you here are aware of, and we're going to be walking you through some of the theoretical aspects of that as well. But before I proceed any further, I'll just try to take a quick minute to introduce myself, what I do and what I'm involved in. So this is a quick profile about myself. I've been involved in the industry for around 8 years now, and I worked with 4 companies in my career, and presently I work as an independent consultant based out of Bangalore. And I also do a lot of corporate trainings for different clients. I train for Walmart Labs, Fidelity Investments, EY. I do a lot of consulting engagements with different startups in the country, and pretty passionate and pretty deeply involved in this field. Just that I started learning data science very early on in my career. Around 2012 is when I got an opportunity. And back that time, we didn't even use the term data science. Back that time, we were basically, we used to call it data mining, right? So I picked it up very early on using R, and then gradually moved into Python, and that's been my journey. And as of now, I'm pretty actively involved in primarily the deep learning and AI aspects of this piece. So let's get started. And just to quickly recap some of the pieces that you already will know, and just to kind of be absolutely sure that all of you understand these pieces. Now, I'm not going to get in too much into data science aspects, but just to kind of focus on statistics. Now, statistics as we know it, in very simple terms, it can be broken into 2 types, right? Primarily, we can break down the core of statistics into two types very broadly. So one type of statistics, we'll call it descriptive, which you already would have learned. We also tend to call it summary statistics. And the other aspect of statistics is what you call inferential, right? These are the 2 pillars of statistics, right? So descriptive statistics basically deals with questions like, hey, what happened and how it happened, right? So descriptive statistics is like looking at data and understanding, okay, what is happening in my data and why is it happening? It's trying to look at a causal analysis. So think of it like asking questions like, hey, what happened? And asking questions like why it happened. All right, it almost as if you can put yourself in the shoes of a doctor. This is you and this is the doctor. All right, so this is you and there goes the doctor. So put yourself on the shoes of a doctor, and let's say you are the data, right? So the doctor is looking at you, and the doctor is able to understand, okay, what is happening? What are some of the symptoms that you're displaying? Okay, what are some of the fundamental symptoms that you're actually displaying? So think of descriptive statistics like a doctor looking at you and saying, okay, what is happening? All right, so let's say I have high temperature, I'm vomiting, I'm showing lots of different symptoms, and doctor is only observing me. Right, that is what summary statistics or descriptive statistics deals with, and it's the simplest kind of statistics that you will probably come across. Right, this is where your mean, median, mode, looking at the distributions, looking at the visualizations, right? Drawing a bar chart and figuring out what are your total sales by different regions. Okay, so probably a simple use case could be looking at a correlation, looking at how profit and sales are correlated. All the basic kind of analytics actually happens here. So descriptive statistics is the basic kind of statistics, the most basic kind of statistics that you will come across. And when I say statistics, when I use the term statistics, many of these terms tend to get misused quite a lot, and it's very overlapping. So when I basically use the term statistics, it's kind of like saying it's kind of like data analysis. Okay, think of it like data analysis. Spelling, I'll just quickly correct the spelling here. So this is statistics. Okay, so data analysis, the science of analyzing data. Okay, in very simple terms, is data analysis. Okay, and obviously statistics is not something we are doing for the first time here. Statistics as a discipline has been around for centuries. The regression term that you will probably learn in your next topic was the first time the term regression was used was back in 1800. So that's how old the field is, and so that's basically what we are dealing with. So the doctor is looking at you and saying, okay, what is happening? What are your symptoms? Now, diagnostic, there's one more kind of statistics that we can call diagnostic, right? So what happened is where you're looking at your data and seeing what is happening. Okay, so I have high temperature, I have high fever, and and diagnostic could be figuring out why it happened. It's getting a little deeper. It's like a causal analysis. So the doctor is doctor is seeing, okay, Shayan has high temperature, he's having high blood pressure. But then, okay, why is it happening? What are the symptoms I can see? But then why are those symptoms actually happening, right? Can I get a little deeper into it, right? So it's like looking at your data, figuring out that northern region is giving you the highest sales. And now you want to get a little deeper and find out why. Okay, so what are the driving factors, right? It's a slightly detailed kind of analytics, and Basically, from a pandas data frame point of view, you can think of it like slicing and dicing your data, doing multi-dimensional analysis and figuring out the causes. Again, it's pretty basic. It's not really, up to this point, you're still pretty much in the basic kind of statistics. Okay, so this is pretty basic stuff that you can pretty much do with your Seaborn and Matplotlib libraries, and it's pretty much asking very basic questions of your data, right? Even causal analysis you can pretty much figure out using fundamental visualization techniques. And we'll do a walkthrough of all these things in our session through multiple case studies. Now comes the inferential part of it. Inferential part is where you're asking more detailed questions. Now the doctor has looked at you, he has seen your symptoms, and he understands why those symptoms are coming. So maybe Sayan has fever. That is the inference he's making in his mind, right? And now he has to basically predict the kind of medication he will give me, right? So this is where the predictive part of analytics actually comes in. So inferential is where you're trying to kind of trying to figure out what is going to happen, right? So what will happen? So descriptive will be what happened, why it happened, and inferential will be more on the lines of what will happen. You are trying to predict an outcome, right? So this is where the inferential part of statistics actually comes in. This is statistics broken into two of its basic branches, something that you probably would have already come across. So here the doctor is trying to basically predict, okay, if I give medication A, this is what will happen. If I give medication B, this is what will happen. The doctor will have a certain null hypothesis and alternate hypothesis in his mind. And basically he's trying to prove it or disprove it. That's the way we're looking at it. Okay, just to connect the dots with this doctor problem and the statistics you would have already learned, right? Now, as I said, statistics is basically data analysis, and the terms gets misused quite a lot. They're pretty much the same thing. So don't be confused when somebody uses the term descriptive statistics and descriptive analytics. They effectively mean the same thing. And I just wanted to kind of present this diagram also to you, and I'm very sure you would have come across this already. But then in case if you have not, this is just to kind of summarize what you have talked about so far. This is basically this is published by Gartner, the analytics maturity in organizations. And what we are basically saying is on the x-axis we have difficulty level and y-axis we have value. Right? As you can see, descriptive analytics is the most basic kind of analytics where the doctor is looking at you and seeing what is happening. Hey, Shayan has high temperature, he has high blood pressure, he has, he's having a very high heartbeat. So these are the symptoms I'm observing. It's the most basic kind of analytics, and as you can see, difficulty level is low, and the overall value chain is also it's pretty low in the value chain overall in the organizations, right? You can't derive much value out of it, and this is the kind of analytics you can do in simple tools, even like Excel, right? Then comes diagnostic, the causal analysis, where the doctor is able to figure out why it's happening. Now you're asking a much more deeper question, that why is it happening? And predictive part is where you're basically looking at what will happen. You're trying to make predictions. And finally, the prescriptive analytics part is the hardest part, where you're trying to kind of write a prescription. Think of it like a doctor writing a prescription saying, okay, if I give medication A, I can cure the disease in 3 days. If I give medication B, I can cure the disease in 5 days. If I give medication C, probably I can cure it in 7 days. And now this is the predictive part of things, right? Predictive is where the doctor is having a model in his mind where he's saying, okay, if I give this medicine, I can cure in this many number of days. He's making a prediction, right? There'll be multiple predictions he'll be making. And then out of all the predictions, he will be giving the optimum prescription. So prescriptive analytics is always the optimization problem. Think of it like an optimization problem. So out of all the medicines, which medicine will the doctor actually choose? What kind of medication or prescription will the doctor choose to kind of, just to be absolutely sure that his objective is kind of met. What is the doctor's objective? And there can be multiple objectives that the doctor might have. One could be to cure the patient in the least amount of time, to make the most amount of money. And there could be so many different types of objective functions that we can actually have. Okay, so these are the 4 broad pillars of analytics, and you go across any organization, you pick up any business domain. As we always say in data science, the problem statement is what forms the key. So you go to any organization, you talk about any business problem. And I always like to say this business problem is always at the forefront of data science, right? And this is extremely important, guys, because coming from a traditional statistics background, anybody who has done classical statistics, I think we can relate to me that classical statistics approaches data science from a very different perspective. If you look at classical statistics always has the question at the forefront. The question is the key. Okay, in classical statistics, the kind of statistics that we probably would have done for a long time, in classical statistics, the question is always the key, right? And when I say the question, I also tend to use the word the hypothesis, right? In classical statistics, the way we have approached things for a long time, the question was always the key. So you ask the question, and on the basis of that, you go back and collect data. So first you ask the question, okay, this is what I want to achieve. And then you go back and collect data, because you have to understand that in the olden days, if you go back a few years, even a few decades, data was very expensive. It was not as easily available as it is today. right? So question was always at the forefront. You first had to narrow down on exactly what you wanted to find out, and then you went out into the world and you collected data. This is extremely important to understand, because from a data science perspective of looking at things, this entire approach is turned on its head. It's kind of totally opposite in today's world, right? So from a data science and machine learning way of looking at things, so I'll probably use the term machine learning here. So from a machine learning way of looking at things, so right now data is the key, and the question is something that we are actually deriving from the data. Here the data is the key, and the question is something that you're deriving from the data. So just to give you an example, you would have already learned about your null and alternate hypothesis, right? Remember, when you are solving all these hypothesis testing questions, you will always define the hypothesis first. It is not that a data is given to you and then you collect hypothesis. No, in a typical real-time scenario, okay, when you're conducting any experiment, right? So hypothesis testing, you have to first set up an experimental setup, you have to conduct, and that's the way you go. The most important part here is you will always want to set up your question first. And I'll give you an example here. Let's do a step. Let's do a an end-to-end hypothesis testing now. Okay. So what I'm trying to get at is, let's say your mean is equal to, let's say your mean is equal to the old mean. This is the old mean. The old mean is equal to 100. What is old mean? Let's say all of you are with upGrad, and upGrad captures a lot of data from you, like depending on the sessions you attend, how much of time you spend, and overall we look at different parameters, and and on the basis of that we will do some analytics on, let's say, how well you can probably perform in a kind of companies we can match you with, and all that kind of stuff, right? We'll do a lot of analytics from our end. Let's say we are tracking mean engagement score. What is this 100? This is the mean engagement score. I'll use the term engagement score. And different platforms will have their own metrics of tracking this thing. You can look at Facebook and Twitter, Instagram. They will track something called popularity score, engagement score. So in Facebook, let's say if you're a very active user, okay, you post very frequently, you get a lot of likes, you've got a lot of connections. LinkedIn, you've got a lot of connections, you're a power connector, so you've got a very good engagement score. So different portals will track these parameters, right? So upGrad also, we have our own parameters of measuring something called an engagement score. So let's say at any point in time, as of this moment, I have the entire historical data of upGrad, and I've actually kind of tracked that the engagement score is equal to 100, right? Engagement score is equal to 100. Now what I want to do is, this is what I already have. Okay, this data I already have. Okay, now what I want to do is, management wants to launch VR, right? So management, they want to launch VR, virtual reality. They want to launch VR, let's say. And just like the domain that we are in right now, machine learning, AI, data science, virtual reality is another extremely popular technology that's picking up in a big way. Pretty much like other digital technologies. So let's say management wants to learn VR. So right now we are doing this session over an online medium, but what if Zoom meeting had a virtual reality component, VR component? I mean, they are building these things. Microsoft, if you are aware of it, they're actually at the forefront of this research. A lot of amazing things are happening in that space, but right now we don't have any full-fledged solutions in my knowledge, right? So let's say we want to experiment with the VR medium, where the professors can come, the faculties can come, the guest lecturers can come and interact with you over VR. Will your engagement improve slightly? That's what we are trying to track, right? This is the question we are framing, right? So it all starts with the question that, hey, you know what? Currently we are having 100 engagement, mean engagement score. If we implement VR, like if I give each of our upGrad learners one VR headset, and if we conduct these sessions over a virtual reality medium, will the overall engagement go up? Will it become slightly better? Imagine you're watching the videos only at home, but what if you could wear a VR goggle and watch those videos? What if it could be more real world? Now, can we drive the engagement higher? That's the kind of question that you're asking. It all starts with a question, and it is precisely on that basis that you set up your null and alternate hypothesis, right? I'm going to come back to the hypothesis testing part of it in a slightly later time. But remember, when you solve these questions and when you set up your hypothesis, it is based on the business problem, right? So the first thing you do is you don't collect data. You first define your hypothesis, right? And this is an extremely important way we approach problems from a statistical point of view, right? But obviously in your course, what you're learning, data science, machine learning, this approach is considered pretty redundant to today's world, but it's very important to appreciate where you actually come from, right? So from a classical statistics way of looking at things, and again, I mean, it's not to say it is not done. Hypothesis testing is still pretty relevant in a lot of organizations, manufacturing organizations, financial organizations, like there are a lot of projects that are still driven by hypothesis testing. It's not to say it's completely redundant, but most aspects of it will be very redundant as you approach machine learning and some of the components of machine learning going forward. And by the time you go to deep learning, this, pretty much all of it you can pretty much kind of scrap and put in a dustbin. So this is, none of this is actually going to be even relevant once you start dealing with billions of hidden features in deep learning. All right, so the most important aspect is you will define the hypothesis. And so what do we have here? If management wants to launch VR, what are we trying to achieve? So what is it that we are trying to achieve here? So what is that, what is that mean that we are trying to achieve? We are looking at something called a new mean, right? If you look at this business problem, the old mean is the original, the old engagement score when people are not wearing VR. I'll say no VR. Okay, and then management wants to launch VR, and in the effect, I want to basically find out some new mean. This is the hypothetical new mean, which I don't know right now. Okay, this is the new mean when people start wearing VR. Okay, I'll say with VR. Remember, I have all the historical data for all of upGrad for this data, for this figure, mu old. I know mu old because this is the database I already have with me. But mu n is something I don't have. I don't know this. Okay, now this is what I was talking about. You don't have this data easily available, right? And so how can you collect this data? New mean is the mean engagement score of all the learners given they are wearing VR devices, right? So at any point in time, let's say at upGrad, we will have 20,000 learners across India, right? So now what we will have to do, if I have to capture the new mean, I will have to give VR devices to each one of you. I will have to capture the scores from each one of you. And on the basis of that, I will calculate new mean. Is that a feasible experiment? Absolutely not, right? Imagine any product launch. How do product launches happen? In product launch, will you straight away launch the product and say, okay, now this is the engagement I'm getting. Okay, it's working, great. It's not working, okay, scrap the product. That's not how product launches happen, right? In product launch, we don't go and launch the product and then decide, okay, no, it's working, it's not working. It's not a descriptive analytics problem, right? So mu n is something I don't have, but I'm trying to estimate what is mu n going to be, right? So I'm trying to do a kind of prediction. I'm trying to make a kind of inference based on some data, right? So how do we define the hypothesis here? Let me test you guys. So what do you think the hypothesis is going to be? Management wants to launch VR, and they have hired me. They have hired me as a statistician to help them in launching VR, right? So I'm the statistician who is who has to perform this experiment from scratch. And let's get away from this usual way where we solve questions, no, where mu n is given, mu 1 is given. Let us look at it from a real-time scenario. How will you go about this experiment? How will you go about setting up this test? So what are your conditions going to be? What are your null and alternate hypothesis going to be? Anybody? So what is an alternate hypothesis, first of all? How do you define an alternate hypothesis? What is an alternate hypothesis? How do you define an alternate hypothesis in the first place? What is the meaning of an alternate hypothesis? Alternate hypothesis, okay, let me just get some answers from you first. Mu mean is less than equal to 100, okay. Okay, so that will be alternate. All right. What is alternate? Let's do it one by one. What is alternate? And one thing I request you not to post on Q&A, because Q&A opens up a different window. Please post all your questions on chat. Please post all your questions on chat, because that is something I'm able to monitor. Yeah. Okay. Against the status quo, that is good. Okay. Alternate is greater than 100. How many of you say okay? I think the confusion will be either greater than 100 or less than 100, right? So I think let's understand what not equal to 100. Somebody says, okay. Complement of null, that is obvious. But my question is, with respect to this problem, now we are away from the theoretical aspects, right? We are away from the theoretical aspect. Theoretically, we know what it is. But now with respect to this business problem, how do we set up our hypothesis? Remember, in statistics, in classical statistics, we first define the hypothesis. Hypothesis means assumption. It is the statement. It's the business problem. So first I define the hypothesis, and then I set up my sample, and then I go about solving it, right? That's the way I go about it. So how do we go about it? Any thoughts? Okay, I assume you guys are aware of hypothesis testing, right? You are all aware of it? Okay. Is a position that states, okay. Okay, current state. Okay, let me give a slightly different twist to it. Basically, the alternate hypothesis is basically what the researcher wants to prove. right? The alternate hypothesis is basically what the researcher wants to prove. So you always look at an alternate hypothesis from the researcher's point of view, from the statistician's point of view. So the statistician, whatever the statistician is trying to prove, you always look at the alternate hypothesis, the concept of alternate hypothesis from the statistician's point of view, right? So with respect to this business problem, what is alternate hypothesis? Alternate hypothesis is going to be mu n is greater than 100. Actually, mu n is greater than mu naught, and mu naught is equal to 100. We already know, right? So this is the way we define the alternate hypothesis. Okay. So what is the null? The null is the complement of that. So whenever we are solving these kind of business problems, we always approach it from an alternate point of view, not from a null point of view, but always from an alternate point of view, right? Exactly. So mu naught will be equal to less than equal to mu naught. Okay. Yes. So we always approach it from an alternate point of view. Alternate is what I'm trying to prove. So what am I trying to prove right now? I'm trying to prove that the new mean, what is the new mean? The new mean is the mean engagement score after everybody starts wearing virtual reality devices, right? So the new mean is the mean engagement score after everybody starts wearing VR devices. That's the way we look at it in simple terms, right? So obviously, what am I trying to prove? I'm trying to prove that the new mean is greater than the old mean. That is what I'm paid. So the company has hired me to prove that, right? Because management wants to launch VR. And because they want to launch VR, they have roped me in and they want me to prove it. They want me to prove this outcome. So we always look at alternate hypothesis from this standpoint. We always explore alternate hypothesis from this standpoint. That management wants to launch VR. I have to help them launch it. So this is what I want to prove. And this is the complement of that. Okay, so this is the first and foremost thing that we actually define in any hypothesis testing problem, right? What is my hypothesis? What is my question? And then I go back and collect data. Okay, so what data will, I hope all of you are clear with this. Why mu n is greater than mu naught? I hope everybody is clear with this. I get a lot of conflicting answers in the chat, but I hope you're all clear. Yeah. Okay, you can look at status quo as well, but it's easier from a business perspective to think of it from a researcher point of view. You always look at it from a researcher point of view, what you're trying to prove. So alternate is what you're trying to prove. Null is always the complement of that, right? I will come to some use cases of one-tailed, two-tailed in a while with you. Okay. Yeah, but this is again assuming that all of you have gone through the fundamental content. If you have not, this is going to be like, all dinosaurs. It will look like all dinosaurs are around. This is possible for null to have less than equal to and greater than equal to. Absolutely, Chanchal. Null can absolutely have less than equal to. In fact, null hypothesis is the only hypothesis condition that can have an equal to sign. You cannot have an equal to coming in alternate, right? Absolutely, null can have equal to. Which is why, Chanchal, just to actually answer your question, we never prove the null is true, right? We always reject the null. So there are only two conditions of hypothesis test, right? What are the two conditions? Either you reject the null or you fail to reject the null, right? So which is why equality can be there in null, which is we never try to prove it. In inferential stats, we never try to prove equality, right? So you can have equality only in null. You can never have equality in alternate, right? Okay. So now that you have defined the hypothesis conditions, what is the next step? The next step is, yeah, exactly. The solution can be thought of as an alternate hypothesis, what you're trying to achieve. Now you go back and now you collect data, right? And this is what I was talking about from a classical statistics standpoint. This is slightly different, right? So you first define the hypothesis, then you collect data. So how will you collect data here? We will set up a small sample of size 25, right? This is the data collection stage. I'll leave it a slightly different color. So now you will go back and take a small sample of size 25 students, right? I will sample 25 students from all of upGrad, and this will be a good representation of all of upGrad's population, right? We have all heard this term that sample should be a good representation of the population. This is exactly how we'll approach this problem. So we will take n equal to 25. Okay. So this is a sample of 25 students in a class. So let's say I gather this sample of 25 students in the class. They're all sitting in this class right now. And for the whole day, we can have any number. I mean, obviously, obviously we can take a different number. That's fine. You want to take 36, we can take 36. I just took an example here. We can take 36. That's fine. I just took 25 because for easier demo. Okay, just for easier mathematics. Okay. All right. So now what we'll do is now we'll measure the engagement scores of each one of them. So for example, this person, I will track what their engagement is: X1, X2, okay, X3, X4, X5. What are these values right now? These values are the engagement scores of each person at the end of the day, right? So what are we doing right now? We are collecting sample data. Population, old mean we have. We are trying to find out the new mean. New mean I don't know. When people, where we are, what will happen, I don't know. This is just like any other product launch. So when, let's say you're trying to launch a new product, what will you do? You will try to test it in your friend circle first. Then you will try to test it in a very small group of neighbors, right? You will give it your known contacts. You will get feedback from them, and then you will roll out into a bigger market. That is true in all product launches. You look at Spotify when it launched in India. I mean, there was a beta trial that was ongoing. It is not that Spotify all of a sudden launched in India, right? They've been experimenting. They've been, tapping the Indian market for quite some period, right? And you look at WhatsApp Pay, look at Google Pay. By the time WhatsApp Pay and Google Pay actually launched, Paytm, MobiKwik, they were already huge players in the country, right? So they had to do a lot of surveys before they actually went ahead with the right product, right? And even now, if you look at Outlook, Gmail, the kind of features they're introducing, Outlook actually has a beta program, and all these have beta programs where you can turn on beta features. Beta features are not they're not rolled out full-fledged, but then you can actually turn it on. It's a beta experience program. It's like a beta testing, you can think of, right? So it is like testing their features in a small group, and if that group likes it, we will roll it out to the larger group. So basically, the question that you're asking right now is, okay, I don't know what will happen in the new mean. I don't know. I cannot procure all the VR devices, give it to everybody, and then test it out. I can't do that. Let me select a small sample of 25 students. Let me procure 25 VR devices. Let me collect their data, and so throughout the whole day, they give you 25 X values. From that, you calculate something called X bar. So let me collect their data. So you basically get an X bar value here. What is the X bar value that you get? Let's say the X bar value that you get is 110. Let's assume you get a sample mean of 110. This is the data that you have collected at the end of one day. Okay. And let's also assume that sigma is equal to 20. Why 20? No reason. This is just an example I'm taking. Let's say sigma equal to 10. Okay, again, why 10? No reason. This is a simple example I'm taking. Okay, so let's say sigma is equal to 10, and you have found out that X bar is equal to 110. This is the data that I've got right now, and this is all that you need to solve your hypothesis testing question. Okay, and again, I'm assuming all of you have some basic background on the topic. I'm only recapping it for you. And let's assume alpha is equal to 5%. Right? What is alpha called? Alpha is called level of significance. Right? Let's say alpha is equal to 5%, right? So as you would have seen, the approach I followed here right now, first I defined my hypothesis, then I went ahead and collected my sample data, 25 students, I gathered in a room, I conducted the test, I took their individual sample values, looked at sample mean, and based on that, I'm trying to make an inference that, hey, should I reject the null or not reject the null? There are only two outcomes in our hypothesis test, right? What are the two outcomes? Either we reject a null or not reject a null. So given this, I would like to give you all, couple of minutes time. So what do you think the right outcome will be? There are only two outcomes in hypothesis test, right? And remember, this is a bit of a mathematical, pen and paper way we are doing it. This is actually important. Why am I doing it this way? Because it is important from an interview perspective, right? In a more real-time scenario, as we get into projects, as we actually get into hands-on and how we actually do things, it's a very different way we do things in a real-world scenario. So remember, there are two different pieces. As I said, classical statistics, you can pretty much put it in a dustbin once you come to artificial intelligence and deep learning concepts with neural nets. None of these things will even be relevant that time. But having said that, this is the topic which we are doing. So I mean, obviously, we are just kind of recapping it. So which is where the pen and paper mode is pretty relevant, because as you know, statistics as a discipline goes back centuries, and that's how we used to do it back then, right? So this kind of a way of working out problems is very common. And oftentimes, if people give you hypothesis testing questions, they will expect you to solve like this, right? So that they'll tell you, okay, hey, how do you decide this? How do you get this mean? Can you do this in pen and paper, right? So that's why we are actually going to make you comfortable with this approach. Okay, so this is all you need for this question. Take a minute. Mu old is 100. Sigma is population standard deviation, right? What is sigma? Sigma is population standard deviation, that is given as 10. N is 25. X bar is equal to 110. And SE, what is SE? All of you know SE, right? I'm going to just go back and write it down for you. All of you know SE. So SE is called a standard error, and standard error is equal to what? What is standard error? Standard error is what? SE is standard error, which is equal to sigma by root n, right? We know this. This is coming from the basically the central limit theorem, right? So standard error will come out to be 10 by 225. Okay, so these are the values that you require for this problem. And the simple question that we are trying to answer is that, hey, you know what, after launching VR, am I seeing a significant increase in my mean engagement score? That after I launched the VR device, do I see a significant increase in my mean engagement score? Originally, mean engagement score was 100. Right now, after I launch VR in this very small group of 25 students, do I see a significant improvement? If I do, that gives me a lot of confidence to go back and tell my management that, hey, you know what, VR is working really well in this very small group. And I think if I launch it all across the globe and all across upGrad, maybe it will be like a big hit. So that's basically from a very common sense perspective how we are looking at inferential stats, right? So it's pretty easy if you think of it. Otherwise, not very scary, all these numbers and mathematical symbols as part of the process, but conceptually, it's a very simple concept. Okay, anybody? Fail to reject, okay? Fail to reject. Anybody else? I just need the answer. How you're solving it, that's okay. That'll be a little difficult to type it out, put it in chat. But what is the outcome? Just put the outcome. Is it reject or fail to reject? That's all I need to know from you. And this is more of me to understand what you have understood already in hypothesis test. Because again, I'm assuming all of you would have gone through the content, right? Yes. Okay. Reject, reject. And again, there are no wrong answers in the class. We are all learning. So it's absolutely fine. It is just for me to gauge your level of understanding. Okay. Fail to reject. All right. Okay. Okay. Fail to reject. Reject. Others? Are all of you calculating or so hopefully all of you are calculating, right? So what do you calculate here? You calculate the t statistic, right? Okay. Fail to reject. Okay. Reject alternate. Okay. 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 Others? How about the others? Okay. While you answer this question, I'll also just give you some time. Parallelly, I'll also try to draw up a few things just to kind of assist you in this answer. I hope the hypothesis conditions are fine to all of you. Reject null and fail to reject null. I hope that part is okay. So you first start with a business problem, and this is what you're trying to prove. So this part, if you're okay, I will just go back and quickly remove this part. And obviously, you guys know what the outcomes are. I'll remove this part. And I will straight away come to the sampling distribution. Okay, reject. Anybody else? Nobody else saying reject? Okay. Okay. Actually, very interesting that you guys are saying reject. The answer is reject null. Okay. Now I'll give you a minute to think about why while I drop the figure. The answer is reject null. In this case, we will reject the null. So people who said reject, you're right. Okay. And the answer is reject null. So we will actually reject null and we will accept alternate. Right. That is the answer to the question. And I will show you why. I will actually accept alternate. Right. Accepting alternate means we will launch the device. That is the answer to the question. Let me drop the figure and show you why it happens. All right. So now, if you look at it, this is basically the summary of what we are trying to achieve. Okay. Just to kind of explain this to you in a very simple manner. And again, there are lots of Python functions and all which are available, which actually helps us achieve these things, which we'll see going forward. But the pen and paper mode is important because this is what actually gets asked. Because when we look at hypothesis testing, we want to understand that you really know what is hypothesis testing. Otherwise, in today's world, if you see, everything is simplified today, right? If you see, there's a function and formula for basically everything. There's a Python function for basically everything. Like for example, correlation, there's a .core function, but then what is correlation? Do you understand correlation? So this is why the pen and paper part is very important, very relevant. Now, first of all, what we are looking at right now is a sampling distribution. It is a sampling distribution. And if you look at it right now, if you look at a sampling distribution, what is mu zero? Mu zero is 100, right? That is the old mean. Mu zero is the old mean. And what kind of a test is this? It is a one-tailed right-tailed test, right? This is basically a one-tailed right-tailed test. Why do we call it a one-tailed right-tailed test? Why do we call it a one-tailed right-tailed test? It's called a one-tailed right-tailed test because we are only checking for one direction, single direction, right? The hypothesis condition is like mu n is greater than mu naught. We are trying to prove whether new mean is greater than the old mean. Is the new mean greater than the old mean? That's what we are trying to prove right now. Okay, so we are checking in a single direction. It's a single directional test, and hence it is a one-tailed right-tailed test. A very simple way. Yes, critical region is on one side, exactly. Similarly, there can be one-tailed left-tailed. There can be two-tailed test. Two-tailed test is on critical region is on both sides. A very simple way of kind of thinking of this problem, if it sounds very confusing, it's like saying that, hey, how high is too high? Okay, management wants to launch VR. When I conduct the experiment, whatever new mean I get, I am basically trying to prove that the new mean is significantly high compared to the old mean. So basically, when you look at this greater than sign is not mathematically greater than. In the world of inferential statistics, this means significantly greater than. What you're trying to prove is the new mean after everybody in the population starts wearing VR is significantly greater than the old mean when nobody is wearing VR. That is what you're trying to prove. So whatever distribution you're seeing here right now, this is the no VR distribution, right? This is the no VR distribution. This is basically where this is the distribution where nobody is wearing VR. This is what we already know. It is centered around 100. We already know this. Now, whatever you observed in your sample, you observed the sample mean is 110. So basically, you observed a distribution that looks somewhat like this. You observed a distribution somewhat like this. And I'll use a slightly different color. This is the distribution that you observed. Right? This is the VR distribution. This is the hypothesized distribution which you think will happen if everybody starts wearing VR. And now the simple question that you're trying to answer is, are these two distributions very spread apart? If it is, then you reject the null. That's what you're trying to intuitively solve. Hypothesis testing at its very core, what you're trying to basically answer here is that, hey, is my new mean significantly high? Now what we are discussing is how significant is too significant? What is that threshold? The threshold is what we define using alpha, which is basically called level of significance, right? And that number you can actually tweak, right? So purely going by a textbook way of solving the question, which you already have learned. So the textbook way of solving the question will be what? So we'll define a critical region. Alpha is 5%, right? And this part is not so relevant. You may have learned it, may not have learned this, but anyways, I will just show you. So I'll go back to my Python quickly. I quickly go back to my Python interface here, and you need to bear with me on this, guys. Okay, so new Python 3. So I'm going to pretty much go and kind of frame this problem in Python quickly for you. Okay, so there goes my stats. I'm going to quickly go and import SciPy stats. Okay, what is SciPy? SciPy is a scientific Python, scientific computation library of Python. A lot of these statistical functions related to t-testing, z-testing, chi-square, ANOVA, a lot of amazing scientific functions are available in SciPy. Okay, I'm going to quickly import the stats module of SciPy, and I'm going to quickly kind of call up this function. SciPy, stats dot norm dot ISF. And don't worry why I'm doing this. I'll explain to you. ISF. All of you have, you know about CDF ISF. If you don't know, that will be different. You have heard about CDF ISF functions, just for my understanding. Otherwise, this might be a little, on a different side. I'll explain to you conceptually, but have you come across okay, fine. Okay, I'll tell you briefly about it. All right, don't worry. Otherwise, it will be getting into a different discussion. Okay, scale is equal to 2. Okay, this is what we have. So basically, what I'm trying to find out here is the critical value. What is stats.norm.isf doing? Stats.norm.isf is simply helping me find a critical value. I will ping this to you. It's no rocket science. As I always say, Python functions are, it's not at all rocket science. It's very straightforward. And what I will do is, not so much about the code, but it's the conceptual part that matters the most. Okay, so what it tells me is what is that critical value. Just observe that number, all of you, 103.289. That's the critical value I'm actually getting. I'll just ping it for you for your reference here on the chat. So I'm getting 103.289. So I will go back to my I'll go back to my note. All I did here was figure out what this critical value will be. This is what I did using this one line of Python code. Okay, now you can argue, Sayan, why did you use Python? We could have used our Z table also. We could have done that. Absolutely, we could have done that. I have simply used the Python function for it. That's the only difference. I've simply used the Python function for it. Right? You can absolutely use your Z table also for this. Okay, up to you how you want to do it. Completely up to you. Right? So all I've done right now is my mean value is around 100. And what I'm trying to find out is what is that critical value? The critical value is coming as 103.28. Now, if my observed sample mean, now this is the way we define the condition. If my observed sample mean is significantly high, is very high. Now we are just saying, okay, hey, how high is too high? How high do you really want to go? If it is really high, now how do you define really high? In this case, 110 is 5 standard deviations above the mean, right? Because 1 SD is 2 units. If you look at 1 SD, it is 2 units. And SD is basically SE, right? 1 SD is 2 units. It's very, so 110 with respect to this normal curve is 5 standard deviations above the mean, which is like more than an outlier. So in this case, it's a very valid question. In this case, there is nothing to think. Straight away, we will say the product is working. So you please go and launch it, right? But then there could be more borderline edge cases, which could come where we define a threshold, right? And now what is that threshold? How do you compute it? That is the function using which we compute it, right? Now we know 103.28 is my threshold. If the observed sample mean is more than that, we can say it is significantly high. If it is not more than that, we say it is not significantly high. This is the mathematical framework that we are discussing, how to solve a hypothesis testing problem. Right? I hope all of you are able to understand. And basically, when the value falls in the critical region, how do we define a critical region? In this case, if the value is like really high, if the value is really high, how high is too high? If it's really high, that's a critical region. That's where I reject the null. It's a rejection zone. I reject the null. That means I say it's having a significant impact. And this zone, what is the other zone called? This is called the acceptance region, right? This is what we call the acceptance region. So this is the critical region and then acceptance region. Acceptance region is where you fail to reject the null. All right. So remember, there are only two possibilities in a hypothesis test. Either you reject the null or you fail to reject the null. In this case, we ended up rejecting the null. Okay. And because I rejected the null, I effectively, it's a complement. So I accept the alternate and then I say, okay, there is a significant change. So mu n is significantly greater than mu naught, which means in English, it means that, hey, you know what, if you launch a device, we are reasonably confident that the new mean, the new engagement score, the new mean engagement score will be significantly higher compared to the old mean engagement score, which means the new distribution will be significantly far away from the old distribution. That's what it basically means, right? Where this is the new mean centered around mu n. Okay, so visually you should be able to think about it. Don't be too confused with the terminology. So visually you should be able to think about it and explain to stakeholders what it actually means in pen and paper, right? Python functions are only helper functions. Even if you're not able to do it, it's still fine. But this conceptual aspect should be absolutely crystal clear. Are all of you clear? People who answered fail to reject null, are all of you clear why it's happening this way? Yes. And hypothesis testing is a domain where you extend to any other kind of business problem. The idea will be the same. Okay. Now, if I had given you a different value right now, it could have been that my value is coming slightly different, right? It could have been that if I slightly change this value, if I make it, let's say if I make it 105, okay, or if I make it, let's say 102. Now, T-stats or CV? T-stats, Jignesh, to answer your question, in T statistic, it will be stats.t.isf, right? So stats.t.isf. All right. So yeah, SciPy has a very common kind of framework across multiple tests, right? Even you'll be surprised, even in F-test, ANOVA, you have the similar kind of function, stats.ftest. ANOVA, we have something called F-test, right? F-statistic. All right. Okay. So by the way, I think some people are used to solving this question with the, usually with the, with the Z statistic approach. Okay. So here I've solved it with the base units, as you can see, 100, 110, 103.28. I've solved with the base units. And some people probably are more comfortable in the original units, right? So you want to solve it with the Z units. And just to give you the understanding how to solve with Z units, in case you're confused that, okay, Sayan, how are you getting 103.28? I want to do it with T table or Z table, then you can do that also, right? That is not very difficult. So let me show you how to do that with the Z table approach. So I'll quickly, okay, I think this part we can keep it as it is. Hold on. Okay, let's keep this part as it is. And I will simply erase the numbers. I will simply erase the numbers from here. Okay. The units I will quickly change here. Okay, I want it to be Z units. So if I convert this to Zscore, what if our value? That's a good question. What if your sample mean was 103.28? In that case, what will you do? You will once again, it's a borderline condition. You will not reject the null. Okay, if it's a borderline, I mean, chances are very low, but then if it happens, you cannot reject null. It's not significant, right? It is not significant. It has to be high. See, the alternate is it has to be greater. So it has to be greater than the critical value, right? So if it is on the borderline, it is not in the critical region, right? You will not reject the null in that case, right? And in a more real-time scenario, although we use 5% threshold, in a more, and see that 5% also depends from case to case, right? From a business perspective, people can actually question you, right? Hey, what can I reduce that number? Can it be 1%? Can it be 2%? Can it be 0.1%? So in a more real-time scenario, you conduct hypothesis tests at multiple alpha values, right? And just to also help you understand, alpha, if you reduce alpha, you are conducting a more stringent test, right? If you have a smaller value of alpha, you are conducting a very strict test. If your alpha value is very high, then it's a very lenient test, right? Think of it that way. If your alpha value is very small, okay, if your alpha value is very small, and give you a real life example here. Let me give you an example here only before I move on to the other problem, right? So let me put down the numbers. Let me put down the numbers. Okay, before that, let me solve this in the Z-score. Then I'll come to the other problem. Okay, so let's say this is zero. What is zero? Zero is basically your mean in Z units, right? This is your mean in Z units, and this is basically your mean in standard units, right? So this is your 2. In standard units, it's going to be like 1 each. Okay, and this value is 5. Why is it 5? Because it is 5 Z-score. All of you are aware of Z-score, I believe, right? So 110 minus 100 divided by 2, right? It is 5 SDs above the mean. So right now it is the same problem I'm solving. Only difference is I'm solving the problem in standard units, in Z units, right? It is 110 minus 100 divided by 2. Okay, so 5 SDs above the mean, and now you're defining, hey, what is the threshold? What is this threshold? So alpha is 5%. So for this value to be 5%, what is this Z-score going to be? That is the other way you can approach the question. So then what is the Z-score going to be? You can either look at the Z table. Are you guys comfortable with Z table? Just for my understanding, you're aware of the Z table? Are you comfortable with the Z table approach, or you're all comfortable with the Z table? So you can solve it that way, or what you can do is you can pretty much come back here and use a log value of 1 and the scale log value of 0 and the scale value of 1. You can do it that way also. Either way you can solve it. Okay, if you go back to the Z table, you will get the same answer. Okay, I can look at a Z table, and I always prefer using a left Z table. This is the Z table left. So I can just go back and show you. It is the same answer I will get. So here I'm getting 2.645. So the threshold is coming out as 2.645. And if we go back and look at the Z table approach, basically we are trying to find out that, hey, 95%, right? So to get 95%, where is 95%? This is the left Z table I have to see, right? Cumulative left Z table. So 5% on right hand side means 95% on left hand side. So 95% will be this, around this range. All right. So left Z table, right? We come back. This is 0.05. Okay. Log of 0. That's why I was wondering why the values are not correct. Yes. So actually log of 0. Why log of 0? Because log of 0 will be mean of 0 and standard deviation of 1. That's why the value. This is 1.645. And if you come back here, you will see 95% is somewhere here between this and this, between this value and this value. Okay. So let's go back and see. It is between this value. I'll try to just type these, make it a bit smaller. So it is basically going to be in the range of, I think it's just scrolling is not working. So it's going to be in the range of 1.64. Hopefully you can see this, right? It's going to be basically 1.64 to 1.65. So I can say it is 1.645, which is the same answer I'm getting here. So there are multiple ways you can solve the question, right? The multiple ways. Don't be confused about the Python function part of it. Python functions you can always memorize, but the concept, the way I actually did this in pen and paper for you, that part should be absolutely clear. How do you How do you solve the hypothesis testing question? That is more important. Right? So what are the, this is going to be 1.645. All right. So then what is the other way we are doing it? Now we are saying that, hey, you know what? 1.645 is the threshold Z-score. If my observed sample mean Z-score is more than that, I will reject the null, else I fail to reject the null. Okay. So in very simple terms, if my value is in the critical region, I will reject it, else I don't reject it. Okay. So this is the way we actually approach a Z-score problem, or basically any hypothesis testing problem. Okay. Why do I call it a Z-test here? Because the sigma is known, and you will basically conduct a t-test when your sigma is unknown, which is what we do in most real-time scenarios. Okay. Okay. Does it mean that Z-test is completely irrelevant? Absolutely not. There are a lot of production processes where sigma will still be known. So for example, if I give you an example of manufacturing, right? Any kind of manufacturing process, typically your standard deviation will be known. If you're manufacturing airline bolts, okay, airline bolts, the mean airline diameter, the machines which are manufacturing these things, right? And as I said, statistics as a discipline has been known for a long time. So if you look at it, there are machines which are manufacturing these bolts. Now there is a set standard deviation that had to be defined. That is based on which your machines are certified to manufacture those bolts in the first place, right? So let's assume golf balls mean diameter is 5 centimeter. You cannot have standard deviation of 4 centimeter. You cannot have it. That kind of a machine will not be approved only. That means on an average, your golf balls can be 9 centimeter versus 1 centimeter. Imagine the error that might get. So standard deviation in manufacturing process often will be fixed, right? And so not always that Z-test is irrelevant, or because people might have a question, a very common question that, okay, Sayan, sigma is something we'll never know. No, in most real-time scenarios, sigma will also be known to you in manufacturing process, even in financial products. How do you define sigma for a financial domain? Like think of mutual fund products. Think of mutual fund products. What is mean? Mean could be, what is the mean returns? Mean returns could be 15%. Mean returns could be 15% for the financial product. Okay. And then standard deviation could be the risk. Standard deviation could be the risk. So how do you define sigma from a financial product standpoint? It could be risk, right? If there is too much of variation, sometimes it gives 15%. Sometimes the small cap funds typically will have a very large sigma value, right? Large cap funds and blue chip funds will have a very small sigma value comparatively, right? They're more reliable funds. So sigma will often be defined in this kind of context. But having said that, in a more real-time scenario, as you get into data science and machine learning components of it, then your Z-testing will not be so relevant. In a real-time scenario, we'll actually conduct t-tests. But whatever I explained to you here, the idea of doing this was to tell you that pen and paper way of doing things is still pretty relevant. And especially from an interview standpoint, when people ask questions, we really like to delve into how you actually understand these things. Otherwise, as I said, there is one line piece of Python code that you can write to get these answers. At the end of the day, what is the summary of all of hypothesis test? If P is less than 5%, you reject, value is significant, else it is not. That is the summary. I mean, even if you don't understand anything about inferential stats, if you can simply memorize that part, that is pretty much the summary of all of inferential stats, right? But then the idea is, do you really understand the depth of it? By the way, just to quickly complete the story, what is the p-value here right now? What is the p-value that we are getting? In this context, in this particular question, what is our p-value? The p-value is this value. The p-value is this particular value. This probability, right? Remember, alpha is this one. What is alpha? Alpha is this one. There goes our alpha, right? Alpha is basically 5%. What is our p-value? The p-value we can also calculate, right? We can actually find out the probability of this value as well. Right? So very, very clearly you can see p-value will be very less. Actually, alpha is 5%. P will be much, much lesser than that. P is the probability to the right-hand side. The blue shaded area is the p-value, right? So if P is less than alpha, we can say that again, we will reject the null. So there are multiple ways you can go about this question. Okay. In a very simple context, what are we saying? We are saying that there are three types of hypothesis conditions you can actually have, right? So from the perspective of VR, virtual reality, this is the problem that we actually solved, right? Where the management is trying to basically figure out, should I launch VR? So what is your alternate hypothesis? Alternate is always what you're trying to prove, right? And here, the kind of test that you always set up is a one-tailed right-tailed test. You always want to set up a one-tailed right-tailed test here. You always want to check in this direction. Your critical value is in this direction. So in simple terms, the question that you're asking is that, hey, you know what? Is it high enough? Think of it from common sense perspective. You will launch VR only when you think it's high enough, right? If the engagement will be high enough, right? How high is too high? That is determined by alpha, right? How high is too high? That is determined by alpha. If alpha value is very low, if alpha value is very low, if alpha is very low, what does it mean? If alpha is very low, then it means you're conducting a very stringent test. You're conducting a very stringent test. Your management has told you that, hey, we don't have enough budgets for VR. So when you tell that is that the test is going to work, so when you say that virtual reality is going to work, you better be sure. There cannot be any edge conditions. You better be sure that virtual reality is going to work. That's the way to think of alpha. That is how you actually set alpha, which is why I said in a real-time scenario, it won't be like solving textbook questions where I give you an alpha and you solve it. The default is 5%, but in a real-time scenario, we actually conduct hypothesis testing for multiple values of alpha. When we give our results to stakeholders, ultimately it's a business decision. So as a statistician, I will give my findings that, hey, alpha equal to 5%, this is what we're getting. There's a 5% chance of error, right? Alpha 10%, 10% chance of error, you will get it. This is what we'll get. Alpha 0.1%, this is the result. Alpha 0.001%, this is my result. So you will basically do hypothesis test for multiple values of alpha. It is not for a single value, we'll do it, right? So typically when the alpha value is very low, what does it mean? What does it mean conceptually? When alpha is very low, conceptually what it means is, conceptually it means that, let me just do this for you. Conceptually, it means that your critical region is extremely small. So this is basically having a very low alpha. And when you have a very low alpha, then you will reject the null only if your sample mean is extremely high. And that means it's a very stringent test. You will launch VR only when your sample mean is like extremely, extremely high. So you're conducting a very stringent test. So just remember that. If alpha is very high, it's a very lenient test. So what does high alpha look like? High alpha looks somewhat like this. High alpha looks somewhat like this. It's a very high alpha. This is like a very high alpha. So here alpha is basically probably, let's say 20%, which is a very meaningless exercise actually. So now the idea is more like, okay, center point is 100 and alpha is like 20%, which is a meaningless exercise actually. Even if your value is 102, even if your sample mean is 102, still you will say that yes, I'm able to, I will reject the null, I will launch the device. So which is a meaningless exercise. You probably end up wasting more money than winning anything. Okay, and you will conduct many lots of these type 1 errors, as we call it. Okay, so this is the way to think of hypothesis test. And what kind of hypothesis test is this called? It's called a one-tail, right-tail test, because you're trying to prove that your value is very high. What is the other kind of test condition that we can actually put? Okay, this is called a one-tail, right-tail test. Just to kind of summarize for all of you, one-tail, right-tail. What is the other kind of test condition we can actually put? We can take another use case. We can take a drug. And by the way, here we learned that this will come on the right-hand side. Let's quickly summarize this for all of you. Okay. Information is a bit of a difficult part, which is why I always like to start this early. So because by the time we go to other interesting aspects, it will be more interesting going forward. But then this is typically a little hard, so I always like to start with this initially. Do we go really low alpha like 0.01? Well, actually, good question, Jignesh. Exactly, medical industry would be where you want to be very sure, right? I think excellent use case you mentioned. I think drug test example we can actually take, right? So for example, you want to launch a drug, right? From the perspective of a drug, null hypothesis, alternate hypothesis. Okay, so this is basically VR launch. This is basically drug launch. Okay, so okay, by the way, just to get the nomenclature right, it's called the one-tail, left-tail test. Okay. And how does it look like? You're basically checking for the left direction, right? So again, please don't memorize these things. It's very logical, very conceptual. The way we look at this problem is, now we are basically kind of looking at all the drugs available in the market, drug me medicine, and we are basically looking at all the dengue drugs available in the market today, right? So dengue is a disease that still we don't have a very known cure for that. But let's say there are some drugs that are out there in the market, and the average cure time of dengue for all the available drugs is, let's say, μ0, and μ0 is equal to, let's say, 7 days right now, whatever drugs you have available in the market. That is a basic market survey that I would have conducted. And I found out that μ0 is equal to 7 days. Mu old is 7 days. That is the average cure time of dengue. So 7 days is the average cure time of dengue for whatever drugs are available in the market today, right? Now management has given me the mandate to basically decide and basically to check whether my new drug is working better than the existing drugs. So, a lot of R&D is happening, and I have come up with this new drug. And now the question is that, hey, should we manufacture this drug wholesale and kind of launch it? Because drug launch is a very expensive exercise, right? We have to kind of, market it, and all those things are there, right? So before I do that, it is like a product launch. I need to be sure that existing drugs are already having a cure time of 7 days. Will my new drug do anything substantially better? So previous question was, will VR increase the value substantially? Now the question is, better means, will my new drug have lesser cure time? Now the question I'm actually asking is, will my new mean be substantially less than my old mean? So the question is slightly different, as you can see right now. So again, I always define my alternate first. What am I trying to prove? I'm trying to prove that my new drug, the average cure time is less than the old drug. So this is how we define the hypothesis conditions once again, and we are conducting this particular test in a left tail direction, as you can see. Okay, hope you can all relate to this, and the same way we can solve this question. So again, first case, how high is too high, and here how low is too low. And finally, from a two-tail perspective, from a two-tail testing perspective, a good example we can take is a typical manufacturing quality control process, where we can say, let's say you're manufacturing bolts or golf balls, right? Let's say we have a machine that is manufacturing golf balls, and the average old diameter of golf balls is 5 centimeter. 5 centimeters is the average old diameter of golf balls that we are manufacturing. Okay, so what is the null hypothesis right now, guys? And what's the alternate? So the problem statement is more like, you already have a machine. You already have a machine that is manufacturing golf balls. This is manufactured by machine A. There's a machine A that has been used for decades in the company. And now the company wants to migrate to a new machine. The company wants to migrate to a new machine, which is more fuel efficient, which is more efficient. Now the question is, before you launch that machine, it is like a product launch. Will you straight away go and launch that machine? No. You want to test that machine out first. I'm sorry, you want to test that machine. You want to see whether it is able to kind of manufacture golf balls with round about the same accuracy, with round about the same diameter. Okay, so how do you go about it? You will launch the machine only if the golf balls manufactured by that new machine are similar, right? So here the hypothesis testing conditions are slightly different. This is how you do it. All right. Center point is, I'm sorry, exactly. Center point is 5. Center point is 5. Sorry. Center point is 5. And what you're basically questioning is, again, think of it from a very, very logical standpoint. What you're asking is that, hey, I will launch my machine. I will launch the new machine only if it is able to manufacture golf balls roundabout similar to what my old machine was already manufacturing. Roundabout in the 5 range. If the new golf balls are too big or too small, the machine is bad. This is bad for me, right? So that is how we define the hypothesis conditions for a two-tailed test. So what kind of hypothesis to design? It is basically totally based on the business problem, right? And this is what I initially wanted to start my discussion with. As I said in statistics, it is always the hypothesis that comes first, right? So you first define the hypothesis, then you collect data, then you look at your sample mean and you say that, hey, you know what, that's my sample mean. So if I know this is my sample mean, from that sample, can I make some inference about the population? And that's basically what the essence of inferential statistics is all about, right? If you have to link it to a very common scenario of the Indian elections, right? And I'm very sure all of us are aware of this piece. So it's a massive exercise that happened only a few months back. So this is the entire population of India, right? And you can read about it. There are some very well-known psephologists in our country. Psephology is the science of studying elections. And the people who do it are called psephologists. Very interesting domain. You can read about it. Okay. A very popular psephologist in our country called Yogendra Yadav. I think it's the next Aam Aadmi Party member. So a lot of interesting thoughts he has actually shared on how, how elections are done and all these things. So you can actually read about it. Very interesting domain. Now, the entire population of India, if you see 100 crore, actually 130 crore plus, but 100 crore was the voter turnout approximately. That is basically what you're trying to predict. So remember, you're trying to make a prediction in the population, right? So you're trying to make some prediction in the population. Okay. So basically you're trying to decide in the population of 100 crore people, which party will win. Party A will win how much votes. That is the problem you're trying to solve right now. Okay. Now, based on that, you define your hypothesis and you collect sample data. What is your sample data? Your sample data is going to be a good representation of population. And if you look at all some of the major exit poll bodies, Chanakya poll and the Republic poll, if you look at all these bodies, they actually publish these things out in the footnotes, how they went about collecting the samples and all these things. Not many of us read these things, but you can read about it. Very interesting field of study. And the sample data that they usually collect, some of the polls that I read about it, they actually put n equal to 25 for each polling booth. Okay, for each polling booth. And this number will add up to probably something close to 1 crore. Something close to 1 crore for the whole sample. So what you're technically trying to do is, you are trying to make some prediction in the population. So you collect sample data. So first you define the problem. Based on the problem, you collect sample data. And in the sample data, all that you do, all the data science work that you talked about, all of the Python, Panda stuff that you have learned so far, all the visualization stuff that you have learned so far, all your EDA, everything, data cleaning, outliers, all the data science life cycle that you have learned about so far, all of it technically happens in your sample. The population is a virtual entity that doesn't even exist. So think of the population like a virtual entity. I'll put it in red. This thing doesn't even exist. This is only a figment of our imagination, that it is something called a population. Of course, I mean, Indian population is something we know it is there, but at any given moment, population is dynamic, population is ever changing. We truly don't know the state of it at any given moment. At any given moment, some person is born, some people are dying. So the population is in a stage of constant flux. We don't know this in reality, right? So from a data science perspective, we always want to find out something in the population that, hey, what will happen? What will happen if I launch my VR? What will happen if I launch my drug? Okay, what is actually going on in 100 crore people? Which party is winning the majority of seats? We are trying to make a prediction in the population, but we are using sample data, right? So all our EDA, everything happens in the sample. And in the sample, we find out that party A, let's say party A wins 70% majority. This is the inference that we are finding out in the sample. Remember, this is what we find out in the sample. All right, this is what we get only in the sample data. Now, we want to find out something in the population, right? So with what we got in the sample, we would have done the usual data science life cycle. We would have gone through the sample, right? So we will basically clean our data cleaning, data transformation. All of these things will happen in our sample data, right? In our sample data. And at the end of it all, what is my inference? I'm getting that party A wins. Let's say party A wins 70% votes. It could be a simple bar chart or a simple descriptive analytics that I did here. All right. And now based on that, I'm trying to infer that, hey, what is actually happening in the population? So in my small sample of 1 crore population, 1 crore sample, I find that party A is winning 70%. So based on that 1 crore, can I guess what is actually happening in 100 crore? And that is what all of inferential stats is all about. Okay. And now this value is called the confidence interval. Right. So what is the confidence interval? Now I can go back and say that I'm 95% confident, 95% confidence that party A wins 65 to 75% votes. Okay, and that's the way you actually kind of go about inferential stats problem. Okay, so you're trying to make some inference upon the population, but you don't know population data you don't have. So you collect a sample, you perform your findings in the sample, and based on what you get in the sample, you're trying to infer about, hey, what is going to happen in the population? What do I think? How much confident am I? I'm 95% confident. I'm not 100% confident. I cannot be, right? In a typical data science perspective, you're never 100% confident about predictions, right? You're only 95% confident that the values will be in this range. That's the way you approach inferential stats. And that's the way you approach any data science project also, which is where the connection actually starts to take shape between data science and stats. So even in a typical data science project, what we do is we start off with some population, right? Population is where we want to make a prediction. So I'm going to slightly tweak the numbers here. So, or maybe I can use a slightly darker color. So population is basically, let's say, this is where we want to predict, let's say predict time taken. Sorry. Ola Cabs is trying to predict how much time it will take to travel from A to B, let's say. So predict time taken to travel from A to B. So remember, this prediction that you're trying to make is in the population. Ultimately, any new customer who books a cab, let's say you'll book a cab tomorrow for the airport. And by the time you book the cab on the app, Ola should show you that, hey, this should take you 20 minutes to reach. Okay, so this time taken prediction, the time taken prediction should happen in the population. Population is dynamic, anybody can book a cab. But when the Ola data scientists are creating a model, ultimately there's a prediction model working behind the scenes. It's a little early to talk about it. There's a regression, other things are involved in this piece, right? But remember, when your data scientists at Ola are creating the model, there has to be some model, right? There has to be some mathematical function that is actually predicting time. Okay, but where are they doing it? Do they have population data? They don't, because population data we don't have, right? So how do they do it? They only have sample data, right? They only have historical data about all the rides that have ever taken place with Ola, right? Probably there are rides that are taking place with Uber also, but Uber will not share their data with Ola, right? So to get the exact accurate time taken, how will they get it? And again, time taken, we can argue that Ola actually uses Google service. That's a different thing. I mean, Ola uses Google service, so Google Maps are actually used. But then we can actually question that, how is Google getting data? Right? How is Google getting data? So probably Google is getting data from people who are using Android services. A lot of other things are there, but not necessarily is Google capturing the whole data, right? So obviously there are 7 billion people on Earth, but are you telling me that Google is able to track movements of all 7 billion people? Absolutely not. Absolutely not. So that is not the population Google is tracking. Google is able to make an inference of how much time it takes to travel from A to B only based on a very small sample of data. Right? People who have opted to share their location with Google, Google also, and it's a very interesting read how Google Maps actually works. Google not only tracks it based on your internet, your 3G and your location, but it also tracks based on mobile signals. Very interesting. I mean, that's another thing that you can read about it. Okay, so there are multiple channels to which Google gets your data, but the idea is it's not the entire data set. Anybody who doesn't have a mobile phone, let's say you just go out and without anything you go on the road, is Google knowing how you're traveling? No, absolutely not, right? You are in a car, you're driving, but you don't have anything. You don't have any cell phones, no electronic devices. Google doesn't have any clue where you are, right? That is also you traveling from A to B, but then Google doesn't have data about you. So technically, sample data is all you're dealing with. You're making your predictions in the sample that, hey, I think this is what is happening in the sample, that on an average, it takes 20 minutes time to travel from this to the airport. So based on that, this is what I think is happening in the population. So that is how all data science projects are also structured. Think of any predictive analytics problem. So you're basically doing all your EDA and all your descriptive and diagnostic analytics on your sample. So on your sample, you will perform all your descriptive and diagnostic analytics. So all of this you will perform in your sample data. This is where you will ask questions like, hey, what happened? What is happening? All of these kind of questions you will answer in the sample. And based on that, on the population, it's a predictive analytics problem you're solving in the population. Okay, it's predictive and prescriptive are typically taking the population data. I hope the initial workflow is clear to all of you, and hope all of you are able to connect the dots of what the different pieces of analytics are, how statistics is related, and basically how we are actually doing this workflow in a real-time perspective. Clear? All of you are okay with this? And with here, we can actually move on to some demos on EDA. Clear? Any questions, guys, that you would like to raise at this point? All of you are clear on this? All right, cool. So let's move on and let's come to some other aspects of our session, and let's come to some of the EDA aspects of our session, which will be a little bit more interesting, because inferential stats is a little bit of a hard topic, but it's very important to get a grasp on this because oftentimes it's the hardest question that get asked, and that differentiates you from the rest. So let's come on to something else. And before that, yeah, okay. Okay, before that, let's come back and let's look at a couple of other aspects of our thing. All right, so what I will do is, Okay, I'll just take up a quick example with all of you. And once again, just to kind of touch base upon what we were initially discussing. So statistics always starts with the question in mind, whereas machine learning and data science that you're doing right now as part of your course, data always at the forefront. So based on data, you're actually writing up the questions. So just be aware of that part, all of you. Now, what we have here is a very interesting data set from something called countries. It's a countries data that we have got right now. And this again is driven by a very popular video that some of you might have come across by a person called Hans Rosling. It's a data visualization video that's very popular on YouTube actually. You can look it up later on, maybe after the session. But if I have to just quickly share the link with you, there's a Hans Rosling, probably would have heard about it. 200 countries. It's a BBC video. You can read about it. Okay, so this is a very interesting video where he talks about the analysis of 200 countries in 4 minutes. You can read about it. I will not play this for you right now. But now what we'll do is we'll actually try to analyze this data and try to basically focus more on the descriptive diagnostic aspects of statistics. Okay, so a couple of things that I would like to stress upon. Some of the things that are actually relevant from an interview and from a actual analytics standpoint, from what you actually use in your real-time scenarios, right? So first things first, I'll just load this in. And the very first kind of plot that we actually see here is a histogram. So I will have a lot of questions for you, right? As I'm discussing this, I'll have a lot of questions for you. So first things first, what is this actually telling you? What is this data actually telling you? If I just had to quickly show this to you, what is this actually telling you? What do the numbers actually tell you? Anybody? You've all read about mean, you've all read about median, right? What do these numbers actually tell you? What do these numbers actually tell you? Okay, that's fine. That's fine. We all know it's central tendency, but my question is, okay, my question is, what do the numbers actually tell you? I mean, it's not obviously central tendency, but what do they tell you? I mean, anything that you can say from this, any kind of skews that you can observe? So can you tell anything about the skews right now? Okay. I think we can actually say that the data is right skewed. Can we say that? Mean and median are very different. That means, okay, so one way we can look at it is we can look at the mean and median values, right? The other way we can do this is we can actually go back and plot a histogram. And basically, what is the generic thing that we have learned? We have learned that if mean is more than median, then it is right skewed. If mean is less than median, is left skewed. That's a general thing that we have learned, right? Very, very basic stuff. But then the idea is, if you look at a histogram, that makes the picture even more clear. If you see right now, very clearly we are able to see that for Asia, we can see that the distribution is extremely right skewed. The distribution is extremely right skewed, highly right skewed. Okay, and it's not surprising because Asia, if you look at it, Asian countries right now, there are very few countries which are extremely rich, right? Whereas if you look at Europe, Europe actually combines Eastern Europe and Western Europe, right? So Europe actually combines Eastern Europe and Western Europe. So Europe is more like normally distributed. I mean, I won't say exactly perfectly normal, but it's not skewed, right? All of you know what skew, right? Skew is a very important concept. You should all understand it, right? So all of you understand skew, right? So this means my data is right skewed. For Asia, it is not only right skewed, it's extremely right skewed. It's very highly right skewed. Okay. And now using your pandas data frame techniques, and actually this is how the questions can actually flow. So I can show the histogram to you, and I can actually ask you that, hey, which are those two countries? Can you figure out? Can you tell me which those two countries are? And you can actually see which those two countries actually are. You can analyze, right? So this is basically 2007 data. Just to show you, this is 2007 data. And if you're curious which those two countries actually are, we can write a little bit of Python code, and we can figure out which those two countries actually are. So this is going to be Asia 2007. Sorry. Asia 2007. And Asia 2007 dot GDP per capita greater than 45,000 probably. I'll probably take 44,000. Maybe it's a small borderline limit. And that will give me a panda series. And now I'm going to be indexing based on that. I'm assuming all of you are comfortable with this kind of notation. Yes, and we'll see it's Kuwait and Singapore. Not very surprising. This is actually 2007 data. It's basically latest as of 2007 data. And I think Kuwait was a very rich country. If you see, if you go back over the years, Kuwait was very rich. Comparative analysis, if you do, Kuwait is a very rich country. Okay. And again, the takeaway from this discussion is something about skewness. Skewness is a very important concept. So please be absolutely clear about how skewness actually is used. Okay. So right skewed, left skewed, and no skew. Very little skew. So another question that often gets asked is, how do you decide the number of bins? On what basis do you decide the number of bins? For example, you can come back here and say 3 bins. Now, even if you take 3 bins, you will get a very high level picture. You will get a very good picture of the distribution of data. And once again, the skew of Asia is really, you can actually it's very prominent right now. If you see, it's extremely prominent, the skew of Asia, if you see. Okay, the skew of Asia is very prominent right now. The skew of Japan is not so prominent. Skew of Europe is not so prominent. The Europe is more symmetrical. You know why? Because Europe actually combines Eastern and Western Europe. Europe actually combines Eastern and Western Europe. That's why it's not so prominent. The distribution is not so prominent. There are equal number of countries which are pretty poor, the equal number of countries which are pretty rich. And what is per capita GDP? Per capita GDP means GDP by population. Think of it that way. India is a big economy. Okay, China is the world's second largest economy. But if you divide by population of China, China's GDP per capita is very low. So China comparatively is very poor. So obviously there are big cities in China, but comparatively it's a very poor country if you look at per population basis, per capita basis. So similarly in Europe, the Eastern Europe is is basically the Soviet Union, the pre-Soviet Union countries, Algeria, those kind of countries which are pretty poor. It's not as compared to the Germany and the France and the Spain, which will come up here in this zone, right? So Europe is reasonably symmetrical, as you can see, and Asia is extremely right skewed. So this is how you actually analyze with histogram. Histogram is an extremely important kind of plotting technique, which you should all be very comfortable with. All right. And it's also what we call a univariate analysis. So there are several things that you get from a histogram. You get to get an idea of the skew, and you also get an idea of your outliers. And as you rightly mentioned, outliers. What are the outliers? Very clearly, Kuwait and Singapore are outliers. Asia, in Asia overall, you can see these are the outlier countries that you're getting. Okay, I can do a slightly deeper analytics, maybe with 33 as a limit, or maybe 30 as a limit. Let's see if I'm getting some more countries here. And I think Hong Kong, China, Kuwait, Singapore are, basically Hong Kong, Kuwait, and Singapore are the outlier countries. And almost every other country is having less than 33,000. You can just imagine the skew of Asia. Okay. So what other things can I do with this data? Let me ask you a question. So basically, oftentimes the question that will come, NEDA, and so far we are discussing inferential, right? Inferential is one part of it. We'll get to see what are the applications of inferential in a while. So far we have done the pen and paper way of doing things. That may be very boring for some of you, but let me tell you, that is the kind of thing that is actually tested. Right? It is a very hard topic, which is why I wanted to take it up in the beginning. But then the idea is there are Python functions, one line of code you can write and you can solve it. In data science, it is hard work, right? So if you're not willing to work hard, then this domain is not for you. So this is the kind of stuff that actually gets asked, right? So we actually will expect you to understand how is confidence interval calculated, what is SE, please do the sampling distribution for me. So sometimes these theoretical questions get asked. Let me absolutely clarify this for you. Right? Otherwise, in a real-time scenario, in your projects, in machine learning, core ML, this is not so relevant, but from a theoretical perspective, because people expect you to understand stats. These kind of questions actually get asked where they will ask you, okay, with pen and paper, you please solve it for me. But then from an implementation perspective, we'll come to that. So please be aware of that part. It is important. So if please recap your inferential stats concepts and how is hypothesis calculated, what is null, what is alternate. These things are very important. All right. Now, what are the other kind of analytics you can do with this data? And a library that I often like to use is Seaborn. Seaborn is one of my most popular libraries. I often like to use Seaborn because matplotlib is kind of a very base plotting library in Python, but I often like to use Seaborn for some of these plots. So what other kind of plotting can you do with this? And oftentimes this is how we'll actually go about doing things. So it is not that I will show you a bar chart and ask you what you see from this. So what I would rather do is, remember, data is the key. It is not the question that is the key. We're in data science mode right now. So now the data forms the key, right? In today's world, there is lots of data, which is not the case when we are doing classical statistics, right? So here data is there. I will show you the data set and I will ask you that, hey, what can you do with this? So then what other kinds of plots can you build for this? Anybody? Maybe SNS dot, you've done SNS, right? Seaborn, have you done Seaborn? Or otherwise it might be a little difficult. Have you done Seaborn? Just for my understanding. Okay, you've done Seaborn, great, okay. All right, so C-bound, you've done box plots, right? So what about box plots, guys? What kind of, okay, what about disk plots? Disk plots are obvious, right? I can do disk plot. Disk plot, what do you want to see? Disk plot of population. What do you expect disk plot of population? Disk plot of population. Disk plot of, let's say, Asia and 2007. Asia 2007 population. So Asia 2007 population, disk plot, I can easily build, right? Let's see. What do you expect a skew? I will not show you. Do you expect a skew? Question for all of you. I will not show the answer. Do you expect a skew? Do you expect a skew right now for this particular plot? Okay, right skew? Right skew we expect? It is tremendously right skewed. And we already know what those two countries are, right? It is India and China. We already know what these two countries are, India, China. Extremely right skewed distribution, Asia, right? Comparatively for Europe, if you see, for Europe, if you see for Europe, Europe is not as right skewed. I mean, obviously it's right skewed. There are a few countries that are extremely populated, highly populated, but then it's not so highly right skewed. Okay. Now my question is, if you look at Asia population, it is extremely right skewed. What do you do with this data right now? How do you correct this skew? The question for all of you is, how do you correct this skew? What do you do with this? See, oftentimes in data science, you would have learned this term that this kind of distribution is bad. Having such skewed distributions is bad. So what do you do here? How do you correct this skew? What do you do here? And by the way, this is population. The same kind of skew you'll find with GDP per capita also. I will find the same kind of skew with GDP per capita also. It is again right skewed, as you can see. Okay, we'll stick to population here. So what do you do with the skew? Skew is happening because of outliers. Absolutely correct. So then how do you handle it? Okay, one way, there are two ways we can deal with this problem, right? We can actually, exactly, we can filter out extreme values, Ankit. But then typically, remember in data science, one very easy way to look at it will be, okay, remove the outliers, remove the extreme values. We can probably go with that. Exactly, work with extreme values separately, right? So one thing we can do is we can actually work with the extreme values separately. We can create a cap. Okay, highly populated countries and low populated countries. We can do it that way. That is one way to separate it out. We can work with the extreme values separately, right? So we'll create a separate data set of outliers. So one very this is one way to do it. The other way to do it is we can actually keep them in the same data set and we can transform them. How? Apply a log transformation, right? We can apply a log transformation. So for example, I can actually go back and apply an np.log. All of you would have heard about a log transformation. If I apply an np.log, what will happen? NP is not defined. Okay, I'll just quickly define NP here. Log has a pretty magical property of reducing right skews. Look at the magic that actually happened here. All I did was I wrapped it around the log transform. In case you're wondering how this happened, just to clarify how this happened and why this happened. So, okay, just quickly go back and show you why this happened here. So I'll take some values here right now for you. Let me take 1, 10, probably I'll take 11, 15, 100, and 1000. Okay, these are my x values. And correspondingly, I'll have log x values. Log x to the base 10, okay? So what is log 1? Log 1 is 0. Log 10 is 1. And this is going to be, let's say, 1.01. This is going to be, let's say, 1.05. That's 2. That's 3. Look at the magic that actually happened here right now. Okay, in the original scales, x was extremely high. There's a tremendous amount of right skew. But when you convert it to log scale, the right skew reduces substantially. And look at these values right now. They become 24. Extremely wonderful transformation we achieved. What was originally tremendously right skewed, these kind of data is very problematic for my machine learning models going forward. It's a little early to talk about it, but just remember, when your data is extremely right skewed, your machine learning model that you build going down the line, going forward, will not give you very good results. So always try to bring them to normal distributions, right? And right now, if we keep just a single log transform, we've been able to transform it to a normal distribution. So logs have a very good property of reducing your skews. And similarly, you can use power transforms also, which are a little advanced way of doing things, feature selection. It's a little early to talk about it right now, but just like log, you can also use power transforms, right? So probably x you can convert to an x squared or an x cube, okay? Or you can probably use a square root transform, root over x, or x third root of cube root, or fourth root of x. Or you can also apply reciprocal transforms. Okay, and together they are actually called box-Cox transforms. You can actually use a method in in Python called box-Cox transforms. You can read about it. Okay, I'm not expecting you to know this right now, but just be aware of it. There are so many things out there. The concept should be clear. What is right skew? How do you deal with right skew? Most of you answered it correctly. We will separate it out. We will deal with it separately. So probably highly populated countries will have different attributes. We will build different machine learning models on them. Low populated countries will have different attributes. We will separate them out. We'll build different machine learning models for them. The other way to do it is you can keep them as part of the same data set, apply a log transform, and work on all of them together. Okay. And is log the only way to do it? No, you can actually apply box-Cox transforms, which all of these transforms together can be worked with it. Okay, so that's the way we actually go about and do it. So this is how you actually handle skews in your data. This is how you handle skews in your data. And if you want to read more about it, you can actually go. There's a very nice blog that I actually came across. So how to convert to normal distribution. Okay, there's a very nice blog I came across. How to convert to normal distribution. You can read about it and transform to normal distribution. Okay, this one. How to transform data to better fit a normal distribution. This actually talks a little bit about the box-Cox transform in case you're not aware of it. Okay, you can read about it. It's a very nice blog that talks about some of these things. Machine Learning Mastery is a good blog. There's another, I think Towards Data Science is something you'll probably know. Another wonderful blog to keep yourself updated with what's happening around data science. So please don't be limited to textbooks. As I always like to say, please don't be limited to textbooks. Textbooks and your content and your course is one way to learn. And these are the power transforms I was talking about, okay? And there is something called, if you go down, you will have something called box-Cox methods we have talked about here, okay? This box-Cox. This is a SciPy function called box-Cox, where all these power transforms are actually used. Okay. All right. Let's move on. And let's come back. Now what we'll do is, now what else can we do? Can we do a box plot here? Can we do a box plot? What are the other kinds of plots we can do? This is the univariate analysis, right, guys? Now, what are the other kinds of plots we can actually do for this? We can do bivariate analysis also, right? What is bivariate analysis? Analysis of two variables, right? Analysis of two variables, we can do a box plot. And box plot of what? What can we analyze here? What do you think? Who will tell me? How can we do a box plot here? How can we do a box plot? X-axis will be, X-axis could be what? We can analyze life expectancy, probably. Yes, box plot is typically one column. We can look at it that way, but box plot can also be bivariate, right? I think the usual way we learn box plot is univariate, but box plot can be bivariate also, right? So what is a bivariate box plot? Let me show you. So X-axis could actually be, let's say, my population. Let's say Y-axis is my continent. And I can actually have a data column, and data could actually be Asia 2007. Okay, there goes my continent. Okay, and I can actually have an SNS box plot. Okay, so this is only Asia, sorry. Let me just put it for the whole world. Where is my data? Okay, I'll just put it for data equal to data. Okay, don't worry about this. Okay, look at this. How amazing is that? So now we are actually looking at data for historically across all the years, and we are comparing population. Maybe I can look at GDP per capita here right now. Per capita GDP. It's a bivariate box plot. Are you guys aware of this bivariate box plot? I think it's a little important that you know this, because box plot can not only be put for a, this is basically a bivariate box plot. So pretty interesting what we are actually seeing right now. Pretty interesting. First of all, lots of outliers for Asia, which is not unexpected, right? And by the way, remember, this is actually for all the years. This is for all the years. So whatever data I've got for all the years. So what I can also do is I can put a simple logic where I can say this is data underscore 2007. And how do I do that? I'll probably put a simple filter, and say data.year is double equal to 2007. Okay, and here I will use only 2007 data. And now what I get is something a little bit more interesting. Obviously, Oceania is basically Australia, New Zealand, and Asia, as you can see, Asia is the median, is good. So how do you interpret this? Question for all of you. How do you interpret this? Anybody would like to explain this to me? How do you interpret this? There are two aspects of interpreting a box plot. So what are the two ways of interpreting a box plot? Who will tell me? How to interpret this? Again, I mean, this is how we'll actually go about it. We'll not tell you what to do, and even the box plot thing, I would, I'll give you a data set and I'll tell you, okay, what are the plots you can build? What is the EDA that you can actually do? Remember, exploratory data analysis is not something where you'll be given a question and people will ask you, okay, draw a bar chart, draw, a pie chart. No. So we'll show you the data. From the data, you have to decide what are the different kinds of plots possible, straightforward. Nobody will tell you plot this, plot that. No, it is exploratory. Remember, the whole nature of EDA is exploratory. So you have to figure out what kind of plots to use, right? No. Let's not get technical. We're not discussing technical. All that is fine. All that is theoretical stuff that you have learned, right? Most of it is basically theoretical stuff. There is quartile, there is 50%, median, range, spread. That's fine. My question is, from a business perspective, how do you go back and how do you share your findings? Hypothesis testing, all the nonsense that we saw some time back was only theoretical, right? Pen and paper way of doing it. But then at the end of the day, how do you go back and give your statements in plain and simple English is what we saw in the last example. Okay, based on sample data, I can go back and say I'm 95% confident that this is what will happen in the population. And based on that, how confident am I that the value will increase? That's the way you interpret it, results in English. In English, what is the interpretation that you can give for Asia here right now? There are two aspects of this business problem, right? Oceania is in good shape, yes. And remember, there are two aspects of the problem. One is a central value. One is for central value. One is central value. What is my central value for a box and whisker plot? It is the median, right? And the other is the variance, the spread. So what is the variance and the spread? The variance and the spread is basically the overall width, the spread of my box and whisker. So as you can see, very interesting. Africa is, the median is also less. And remember, this is per capita GDP. Africa, the median is also less and the variance is also very less. So African countries are on an average very poor compared to the rest of the world, even compared to Asia and Americas. And by the way, Americas, you might be wondering, why is it so less? Because Americas actually includes your North America and South America both. Okay. And very clearly, you might have guessed what these two outliers actually are. These two outliers are US and Canada, right? And here you have Brazil, Argentina, Colombia, all the other countries are coming here, right? So the way to interpret this is two aspects. Central value, so you'll say median of Africa is very less compared to the rest of the countries, and the spread of Africa is also very less. So Africa, almost on an average, all the countries are poor compared to other countries like Kenya and South Africa, which will be probably a little richer. Okay, and then Asia is very interesting. Asia, the median is low, but the variance is huge. The skew is massive. And very interesting, Europe is also highly skewed. Why? Because Europe, remember, the variance is very high. Why is the variance very high for Europe? Because Europe includes Eastern and Western Europe both, right? So the median is very high. Median is very high because the France and the Spain and the Germany and the Italy, they have kind of pulled the median high. Okay, but then there are a lot of values that are actually coming below this as well. This is our Eastern Europe, which are comparatively pretty poor if you see compared to the rest of the values. Okay, all right. So this is the way we can actually look at a bivariate box and whisker plot. Univariate you probably would have seen, and there are so many ways we can look at this analysis. And another way we can analyze this is basically based on probably year to some extent. So we can, instead of putting it as a continent, we can probably put it as based on year. And here we can actually take the whole data. We can take the whole data. This is a very interesting analysis actually, if I do it based on year. So y-axis will be actually year. Okay, and let me just show you how this works out. Okay, small. Okay. Okay, I'm just going to quickly go back and change the orientation here. Okay, what you're seeing is something very interesting. Now, who will interpret this for me? This is again a very interesting kind of plot. Anybody would like to interpret this for me? So once again, as you can see, over the years, what are we seeing right now over the years? Over the years, we can see that as the years have progressed, the per capita GDP of all the countries have kind of risen. On an average, they have risen. Year to year, they've improved. So not only have the median values improved, so when you look at the box and whisker, please focus on the median values. The median values on an average have improved, and the variance also has increased. That means there are two interpretations we can actually give for this. One is on an average, the per capita GDP has improved. That means the countries have got richer over the years on an average. And what else? What is the other interpretation of variance? How do you interpret variance here right now? In English. In English, how do you interpret variance? How do we interpret variance in English? So the spread is also very high, right? As you can see from year, over the years, the values have actually increased significantly. So this is again a more countries have growth. No, gap between rich and poor has increased. Exactly. Maybe there is more inequality in the world. That's the way we can look at it, right? So 1952 to 2007, the inequality has actually increased. So yes, countries on an average, on the median value has increased significantly. The central value on an average, it is greater, right? But the inequality has also risen. That means there is more variance in the incomes in the countries. So think of it that way. Beautiful. So there's several ways you can do this analysis. So remember, disk plots, box plots are extremely important from an interview and from an actual implementation standpoint. Okay. And another kind of plot that I would really like to stress upon is basically your pair plot. So pair plots are also extremely important. So if I just quickly do a pair plot here for you. So this is what a pair plot looks like. So let me show you only for only for 2007. That will be simpler to look at. Okay, this is what a pair plot looks like. And I'll probably go back and do a diag kind equal to KDE. Again, a very important kind of plot from a data science perspective. All right, here it goes. So what do you actually see from this? Once again, please ignore the year column. The year column is not very relevant. Now, if you look at it right now, if you focus on the bottom half of the pair plot, what it tells you in one shot, it gives you a beautiful relationship between the variables. Extremely important. I can't stress upon how important pair plots actually are. And again, it's a little early to talk about it, how they are used in a machine learning context. But these kind of plots are extremely useful from a machine learning context. When you're solving classification problems, regression problems, it is very important. First of all, straight away out of the box, the diagonals will give you the distribution plots, right? You can see the data is not normal. So first of all, you can use it for normalization purpose. And two, it tells you the relationship between variables. So probably GDP per capita and life expectancy, you can see it's not a linear relationship. It's a logarithmic relationship, right? So straight away, you can get an idea about what kind of transformation to apply to make it more linear, right? So next topic you will do is linear regression. So if you see these kind of relationships, then the straightforward thing to note that linear regression straight away out of the box you cannot apply, because the relationship is not linear. Your data is not linear. And if you look at it this way, you can see life expectancy and per capita GDP, it is not linear. It is kind of, going this way. So you need to transform these into linear distributions. Okay, so this is a very important kind of plot that you will be using quite a lot in your real-time scenario. All right, what I would like to do here, I would like to take you back to a very interesting case study, and just to kind of help you understand how to approach these kind of problems. Now, what we are looking at right now is a, obviously is a loan prediction problem, a problem that is very interesting and growing in a big way today. Obviously, we are still a long way away from implementing machine learning in commercial banking. A lot of privacy issues and a lot of concerns are there, because machine learning models, one thing that we know about them is the results that they give out are mostly not explainable, right? You can't often explain the kind of results that are actually given out. So model will predict, okay, person should not be given a loan, whereas in reality, you should have given a loan to a person. Okay, so I will not get too much into that aspect of things, but here the objective is more to look at the EDA aspect and how to basically look at a data set and what kind of analytics we can actually apply, right? So as you can see, just to kind of go over the problem statement, Dream Housing Finance Company deals in on home loans. They have presence across all urban, semi-urban, rural areas, and customers will apply for a home loan. And based on that, the company wants to automate the loan eligibility process. If you look at how they are, if you look at the process of how they are done nowadays, most of it, especially in India, I think it's a very, a lot of paperwork is involved. Very recently, ICICI Bank went ahead and automated their process. If you see now you can actually apply for a home loan. People are not aware, probably home loans up to 1 crore you can get through internet banking, right? It's a pretty amazing facility that they launched only a few months back. But then largely it's a very manual process. You have to give a lot of documents and all. And a lot of a lot of manual intervention is there, where a loan officer gets to decide whether you get the loan or not. There's no real machine learning that's happening here in today's world, especially in loan prediction. Okay, but let's say the company wants to automate that process, and based on that, they are collecting all these details, right? They're collecting gender, marital status, education, how many dependents you have, income, and all these things. And all these things we are actually doing. All these things we are doing to kind of automate the process. Now the idea is what kind of data we have. Just to quickly show you: loan ID, gender, married, dependents, education, self-employed, applicant income, co-applicant income, loan amount, loan amount term, credit history, property area, and finally loan status, right? So loan status is basically what we are trying to decide, right? So what are we trying to find out right now? We are trying to find out the loan status. If you think of it from a real world perspective, again, this is how things are going to pretty much look like. From an actual implementation point of view, obviously, and from an interview point of view, we will not be giving you simple data sets. As I told you, like most likely it will be a case study where you're given a problem statement and you're asked to first of all decide that, hey, what are your hypotheses? Remember, initially when these kind of questions are given to you, you will not even be shown this data set. We'll actually ask you that, hey, in order to predict loans, what do you think the right feature should be? Remember, in data, this is where you actually start with the question. This is where you have to decide what the most important features are, and then you go out and collect data, and then you go back and collect data. Okay, this is what data I need. So based on logic, I think we can figure out for loan prediction what kind of data is important, right? Obviously, we need credit score, we need income, right? We need recent transactions, net worth. These are very obvious fields, right? We need marital status. And now this is what my data set is given to me. And on the basis of that, you will need to go back and do some EDA, right? So what kind of EDA can we actually do? And again, I think the time is little limited. So just to kind of give you the approach here. So how do we go about it? First, please be aware of it. Please, even before you see the dataset, you have to absolutely define the hypothesis. Hypothesis basically means what are the factors that you think are driving the loan process? What are the factors that you think will help the bank decide whether you should give loan to a person or not? Sometimes in data science, it's a very common problem. As I work in so many projects, I can relate to from my experience. Oftentimes, problem statements are framed. Customers will not have a clue of what data is available. Managers will certainly not have a clue. Oftentimes, you are left in a scenario where somebody wants you to kind of close some project, and you will have to do it. Whether your data is there, not there, doesn't matter. You will actually have to complete the project. Oftentimes, you will end up in a scenario where in order to solve a business problem, you will need to collect data, but the data is not available. But even then, you should have a hypothesis that, okay, I think income or I think credit rating is an extremely important field that helps me in predicting whether a loan should be given to a person or not. Whether the data is available or not is the next question, but having that hypothesis is very important. And these are some of the most important questions that often get asked, where, even before we get into the process of, getting into deciding, looking at data and doing our usual EDA on our data with Python, we actually ask you, what do you think are the right variables? And then we go about it. So moving on, now what we do is we look at total number of rows. This is the usual info method that we do. And now count plots. What are count plots used for? Hopefully all of you would have seen count plots, right? Hopefully all of you would have seen count plots, right? What are count plots used for? Who will tell me what are count plots used for? So for example, if I do count plot of gender, what do you think it will give me? Frequency, exactly. Count plots are very much like histograms, right? So there are multiple ways of doing the same thing. As we say in Python code, there are multiple ways of doing the same thing. So count plots are basically frequency. So very interesting observations I'm actually getting. And as and when I'm getting these observations, I'm also tallying them up in a small notebook below. So obviously there are more males that have actually applied for loans, and there are probably more married folks that have actually applied for loans. What's that? Okay. And now dependents. There are, probably if you look at it, the more graduate people who actually applied for loans. Okay. So this is the basic EDA that we can actually do, and what we can, and this is how we actually go about it. Now, again, I won't get into all the, the variables here, but just to kind of show you how we actually report our findings. This is the way we actually report our findings. 82% males and nearly 18% females. So mostly the people who applied for loans are males. That tells me something very interesting. Probably that leads to some bias. I don't know. That this is only the data telling a story, right? This is only the data telling me the story. So this is basically based on what I'm seeing in my data. Okay. Married people count is more in comparison to bachelors. Okay. Independents count is 0. So maybe most people who are applying for loans are having 0 dependents, right? And if you see, very interesting, urban people, I mean, rural people is lesser, obviously, that is there, right? So these are the kind of things that are actually important. Why? Let me tell you why. Because when you look at this kind of stuff, it is important for you to gather more data where people with lesser credit history are also applying for loans. That is very important, right? So when you look at self-employed people are not taking loans. So when you're building your models, it is very important that you're actually having an equal distribution of data. So this kind of EDA is also very important, right? You should have a sense of, okay, what my distributions actually are. All right. And this is how I'm actually simply tabulating my results right now. Okay. And now, very interesting, applicant income, if you see, it's an extremely right skew distribution. We have already seen how to handle right skews. It's not surprising, right? Applicant income, if you see, extremely right skew distribution. And if you look at the box and whisker plot, again, if you see, it's a highly right skew distribution. Whatever data set I'm presenting to you right now, it is actually from a competition. It's a Kaggle competition. Now, again, I think time is limited. I cannot get into the machine learning parts of it, but that's a different piece. But this is primarily just to tell you why EDA is important, right? So I cannot straight away use this to build a machine learning model. What is the final outcome of this particular project? The final outcome is when a new data is given to me, when a new loan applicant comes into my system, and on the basis of the different parameters, like let's say loan ID, gender, married, dependents, education, self-employed, on the basis of that, I can actually predict whether the loan status is yes or no. That is basically the idea of that we are trying to make. All right. So moving on, applicant income, very interesting. I think this is the other kind of EDA that we can actually do. And look at this. What is the observation you get from this, guys? Very interesting question for all of you. This is again you would have seen in all these examples, there are certain kinds of plots which are so important. One is this is the disk plot, and there is the box and whisker plot. Okay. Graduate and not graduate. So graduate, there are lots of outliers we're seeing for graduate, right? You will see there are lots of outliers we're seeing for graduates. And also very interesting, graduate people typically tend to have higher incomes, not very surprising, right? So graduates typically tend to have higher applicant incomes. And obviously there are more outliers we are seeing for graduates. It's not very surprising, right? So what is the observation we're getting? That graduates are commanding a better pay packet. Not surprising. I think this is what we expect. Okay. And also very interesting. This is co-applicant income versus loan status. So obviously income and loan status we can actually understand, right? If the co-applicant income is high, if the co-applicant income is very high, turns out loan status is no. That is a very interesting finding actually. So you can actually see that, the findings you're actually getting from this. All right. And another thing that I wanted to show you is this one. This is also very interesting. Look at this. This is applicant income versus loan status. I think this is obvious, right? What the interpretation here is obvious, that obviously if your applicant income is, high income group is comparatively preferred for loans, which is obvious, right? If you see the red line, the blue line is basically where loans are given, and the median income is slightly higher, not very high, but it's slightly higher. Very interesting. This guy was not given a loan. And this is the kind of analysis that I would actually like to do. That, okay, this person's income is so high and yet he's not given a loan. Remember, EDA is all about the analysis part that happens before data science or before you start building your models, right? So there is no defined way of doing it. If you're asking for a framework, there is no defined way of doing it. But then you will have to have an understanding that, okay, I have a data frame with 10, 15 columns, and these are my numerical columns. These are my categorical columns. Okay. And this is the kind of plots I need to build for this, right? And right now, as you would have seen in all of our examples so far, we are focused heavily on the box and whisker plot because they are implementation scenario. All right, distribution plots and box and whisker plots. All right, what else can we get? These are our count plots, and I think obvious interpretations we can get from this as well. Gender wise, loan status. Okay, naturally males are the higher in number, and comparatively, you can also get an idea about the frequency or the percentage of loans that are accepted or rejected based on the different gender groups. All right. So this is also very interesting. This is the correlation matrix. Why is correlation matrix important? Correlation is something that you would have already learned, right? Correlation exists between two numerical variables, right? So why is correlation important, guys? Because if two variables are correlated, then you can build a better regression model to actually predict, right? For example, from a prediction point of view, what are the two golden rules of predicting y from x? Let's look at this right now. So we have got, let's say we want to predict an input. You've got an output here, and we have an input here right now. Okay, I'll take a simple regression problem. Let's say there's some y equal to fx that we have here. Okay, well, let me take some input and output. The idea is the output should have strong correlation, with input. Now, once again, what I'm touching upon right now might be a little difficult for you to grasp, but this is again how we go back and do things from a machine learning perspective. See, otherwise it is just like saying EDA, we do the plots and that's it, the story is over. No, these are things. It's not just like you're learning as a textbook and you're learning some topics in a class, do some quizzes, assignments, and you feel like you've learned everything. It's not. That's meaningless. But all of this you do is from the perspective of how you build models going forward, right? When you're building your machine learning models, you will have some output variable, right? That output variable is what you're trying to predict. The input are the features based on what you're trying to predict. In the context of this problem, the output is you're deciding whether you should give the loan or not. The input is basically the different features like applicant income, you have the gender, all these different aspects are there, right? Now, how can we check correlation kind of matrix for categorical variables? Well, Khushbu, that's a good question. Technically, for categorical variable, you don't have anything called correlation. We use a chi-square test. I'll show you what a chi-square test is. Probably you would have done this. If not, I'll give you a one-line piece of code through which you can do chi-square test. Okay. Okay. So correlation is only defined for numerical variables, not for categorical variables, right? And what is the other thing we do here? So output should have strong correlation with input, and or features should not be correlated. Should not be correlated. So output should have strong correlation, but input should not be correlated. Input should have no correlation. Ideally, the correlation should be as less as possible. That's the way to look at it. Okay. Now, what we do is, so as if you see right now, do you see any strong correlation between the inputs right now? I think loan amount and applicant income, you can see a very strong correlation. Otherwise, there is very limited correlation we are seeing. 0.57 correlation we're seeing, right? And I think the techniques you would have been taught so far is, okay, if you see a strong correlation, then remove that variable, right? All that stuff you never learned, right? In a more real-time scenario, I can tell you we don't drop features, right? Feature selection is a very deep area, right? So technically, we don't drop features, okay? So the idea is, yes, probably if you see, there are two features, F1 and F2. Just to give you a slightly different dimension, if you know that F1 and F2 are highly correlated, then you don't drop it, okay? Please don't drop the features. That is the easiest way to look at it, right? But please don't drop the features, right? You will technically do something called PCA. Have you learned PCA? Maybe not. So you technically do PCA and you will try to create hidden features, right? You do feature extraction, right? Yes, from what you have learned so far for your questions and other things, you can just probably, that's one basic way to do it. But in a real-time implementation perspective, we never drop features, right? Because it might happen that feature 1 and feature 2 might have some basic hidden relationship that is there, which we will not drop. We will not drop feature 1. On one hand, we are doing machine learning where we are saying we don't know the rules. Okay, so just based on collinearity and these kind of concepts, we will not say that there is a relationship, so let's drop the features. No, we don't do it that way, right? Rather, what we do is we use the two features and we find out some hidden features. And this technique is a little deep technique called feature extraction. Feature extraction. Right? Feature extraction. See, straight away out of the box with domain knowledge, you can go ahead and remove some features. I mean, let's say, for example, if you have got, let's say, you've got size in meter square and you've got a variable of size in feet square. You've got two different variables, okay? And using these two features, you're trying to predict, let's say, size of the house, price of the house. What is the housing price? right? So you got two different variables, size in meter square, size in feet square, and based on that, you try to predict price of the house. Now, size in meter square and size in feet square, they are all highly correlated variables, right? They're all highly correlated variables. So obviously, in this case, it's with domain knowledge, you can say it's the formula that will link the two, right? So you can straight away drop one of them. Okay, but otherwise, in a more real-time scenario, you will not drop variables like this. You will use better techniques like PCA and other things to actually drop variables. So please don't just say kind of just from like theoretical stuff say that we'll drop variables. All right, now, okay. Now what I will do is just to kind of cover up some of the questions that you actually had on how we actually go back and do this. Okay, so a question for you. This is more of a question that I have for all of you here. So how do we look at relationship between, let me just create a matrix for you. This is numerical. So this is input. Let me put it like this. Numerical, numerical. How do you look at relationship between two numerical variables? That will be correlation, right? That is something all of you are aware of. Correlation. Now I have a slightly different question for you. How do you look at relationship between numerical and categorical variables? Something that you may not know. Little bit of a hard question. How do you look at relationship between, I want a metric, not just a box plot. It's not a visualization question. Obviously visualization we already saw, right? Valid point. But then how do you look at numerical categorical and how do you look at categorical? I'm not talking about, creating a plot here. Plot we are done, right? Plot all of you are comfortable, reasonably okay, right? But now hard metrics. It is just like if we look at correlation, we'll find a very strong correlation between two features and we'll say the features are correlated. So on that basis, how can I say there exists a very strong correlation between a numeric and a categorical variable? How can I frame that statement? Okay, that way we can do it. You have learned about one-hot encoding, right? That's again a very basic way of doing things. But then how do you actually go back and do it? We can actually use ANOVA for this. It's slightly advanced what I'm talking about right now, but the whole point is to make the session advanced. Otherwise, we'll be in basic territory only, right? Okay, so let me get a little bit into how this is actually done. All right. So how do you actually mathematically calculate or how do you give a, how do you use a p-value technique to tell whether exists a significant relationship between a numerical and a categorical variable? So let me take a simple example here. What we'll do is, let me come back to this example. Are you aware of this? I'm not sure if you're aware of this. I'm surprised if you don't know this actually. Are you aware of this? How to do this? You've done ANOVA, right? Just for my understanding, guys. Okay. I think you would have done ANOVA. Okay. ANOVA is just like a multi-tail t-test. Think of it that way. It's just like a, okay. I think it's part of an additional read, but that's okay. The idea here is, I mean, it's one thing to know hypothesis testing. Hypothesis testing is what we did some time back, right? That's fine. I think ANOVA is part of your is part of an additional read that is there for you. All right. It is very much like t-testing. Okay. But as I said, hypothesis testing it's one way to look at hypothesis testing is what we solved some time back with a conceptual, pen and paper approach. But going forward, whatever you do with hypothesis testing and how you use the statistical tests will be purely from a Python function standpoint, right? Where we straight away look at some Python functions, how we call certain Python functions, and how we look at their outputs. How can we interpret the outputs? So that is how we'll actually approach this question now. So let me give you a simple data set here. It's a simple data set where we are seeing 3 different types of gyms. Okay, I'll just show you my data set here quickly. All right, this is a bit of a hard topic. Okay, what I'm getting into right now, I don't have to get into this, but just to kind of make it a bit more, just so that you learn something out of the session. It's like, okay. So, okay, so if I just have to quickly print this out, monthly income df dot head, just going to print out all the values here for you. Okay, now what you have right now are 2 variables, right? There's a gym variable, there's a monthly income variable. Okay, these are the 2 variables you've got right now. There's a gym variable and there's a monthly income variable. Gym is a categorical variable, all of you can relate to that, and monthly income is a numerical variable. There's a categorical and there's a numerical variable we have got right now. What we are trying to do here, is we are trying to figure out that, hey, does there exist a relationship between the gym and the monthly income type? It's very logical, no? Think of it this way. if you know a person goes to a particular kind of gym, can you really say the person earns a higher salary or a lower salary? Does it even make sense? Think of it that way. Does it even make sense? Now, one way we can do this, as you rightly said, we can actually look at a box and whisker plot, right? Now, the box and whisker plot is actually telling us that there is no relationship. Visually only we can say there is no relationship. Now what we are doing is, obviously there is no relationship, right? You can see that we are plotting monthly income along the y-axis, gym along the x-axis. We are seeing no relationship. But what I want to do is, I want to use hypothesis test and t-testing technique to tell me, does there exist a relationship? All of you have done 2 sample t-tests, right? Just from understanding. 2 sample t-tests you will probably know, right? Where you're comparing 2 different samples. Gym 1, gym 2, which gym is high, okay? Is there a significant difference, right? So it's like saying you're comparing gym A and gym B. Gym A and gym B. So what do? You basically have a gym A distribution and you have a gym B distribution. These are the 2 different distributions you have. And the question that you're asking is that, hey, is the mean of gym A very different from the mean of gym B? That's the question we are asking, right? In all of hypothesis testing, the fundamental question that we are asking is, are the values significantly different? Is B significantly higher than A? Is A significantly higher than B? It is not mathematically greater, it is significantly greater, right? Only difference in ANOVA is that in ANOVA you're having multiple samples, right? So basically here you have only A and B. In 2 sample t-tests, you didn't tell your 2 values you're comparing, right? In ANOVA, you're basically having a third variable C. In the world of ANOVA right now, you basically have this, where your gym A, gym B, and gym C look like this. So if I have to plot a similar distribution plot for this, your distribution plot here basically looks somewhat like this. There goes your gym A, there goes your gym B, there goes your gym C. There goes your A, B, and C respectively. Okay, just to kind of help you understand what this context is. All right, these are overlapping plots. And why overlapping? Because naturally, I'm not seeing any difference in the incomes. All the gyms have entered the same distribution of incomes, right? So ANOVA is basically the same kind of thing, just that we are doing multiple t-tests, right? ANOVA is like multiple 2 sample t-tests we are doing. So one with gym 1 and gym 2, one with gym 2 and gym 3, and one with gym 1 and gym 3. Think of it that way. Now, what I will straight away do is, I will straight away take you to my ANOVA implementation. This is not required. None of the theory is required. Okay, just be aware of how to use it. Okay, this is where we actually slowly start to come into how are some of these hypothesis testing stuff actually used. Just like what we saw, how is EDA used? In EDA, what are the important things you should know? You should know outliers, you should know distribution plots, skew. Okay, please be very, very clear on skewness, how to remove the skew, log transform, box-Cox transforms. Please be very clear on those topics. Please be very clear on missing values. Okay, these are absolutely important stuff in your implementation stuff. All right. Now, this is how we actually use ANOVA and t-testing in our real-time scenario. All right. Now, if you look at the output, we are seeing a p-value of 0.61. P-value should be less than 5%, right? So if P is less than 5, we can say feature is significant. Okay. As I said, what is the takeaway from all of inferential stats? The takeaway is, if P is less than 5%, then feature is significant. Okay, if you understand nothing about inferential stats and hypothesis testing, this is the one takeaway you should have, and everything else will be fine. Okay, that doesn't mean you should not know it. You should understand it well, but otherwise, this is what you will actually get used going forward. Right? You will run a straight away ANOVA test. Monthly income is what you're trying to predict. Gym is the feature or independent variable that you have got right now. That is how you frame it. Calculate your p-value. Your p-value is coming as less than 5%. Remember, 5% is 0.05, 0.61 is much greater than that. That means feature is not significant here. That means gym is not a significant predictor of monthly income. Gym is not a significant predictor of monthly income. That's the way we actually put this in English. And when it's not a significant predictor, it's like saying gym is not that highly correlated with monthly income. If I know the gym of a person, I cannot predict his monthly income. And that's the way we look at it. So we straight away look at the p-values right now. That is how we'll do all our analysis going forward. Now, why is this important? You might ask me, Sayan, why are we even learning this? Because again, as I said, when you're building a machine learning models going forward, so going forward, when you start building a machine learning models, you will choose only those features only those features that have a strong correlation with your output. Because obviously, if gym is not a good predictor of monthly income, then you will not include gym as part of your model. You will include more relevant parameters like experience. If you're trying to predict salary of a person, experience is more important. Which company they work in is more important. Probably which society they stay in is more important. Okay, this is where we get to the guesstimate part of things, where I ask you, okay, hey, this is what you have to predict. Tell me what are the variables required. Okay, maybe I should know how many dependents the person have. What is the age of the person? Right? What is the qualifications of the person? The person is a PhD, maybe they will have a higher salary probably in some way. Okay, so this is what is actually gym is not. Gym is not. Okay, visually I'm saying is, and now statistically I've established it. Okay, now if I give you a slightly different example, just to really help you understand and connect the dots. Okay, so this is one more example I can show you. So this is the mean pressure DF. This is also a very interesting example actually. This comes from the idea of this example is National Transportation Safety Board. It examines the safety and of compact cars, mid-size cars, and full-size cars. So what does it do? It conducts crash tests. It conducts crash tests on all these three different types of cars. And if you look at the visual results here, I think the answer is obvious. So basically, you've got a car type and the mean pressure. What is the problem statement we have got? We are trying to establish a relationship between car type and mean pressure. We are saying, is car type and mean pressure related? Is the categorical and the numerical variable related? So do we find a relationship? What do you see? I think it's an obvious question. This one is very, very obvious. It's obvious, right? So car type C is the compact car. I think it means that it's a very compact car. It's a Tata Nano. And if you subject a Tata Nano to a crash test, the Tata Nano will completely completely compress. Think of it that way. And comparatively, if you have a bigger car, if you have a full size car, with a bigger car like a Toyota Innova, and if you subject that to a crash test, then obviously the Toyota Innova will survive much better. The pressure is much lesser than the car. Think of it that way. So visually, I can find a very meaningful separation. That means definitely the type of car has something to do with mean pressure, right? What kind of car you have, that affects the kind of pressure that is actually applied on your car when the crash test is actually performed. Okay, I think it's very obvious. So visually only I can find a difference. But then we are discussing statistics here. We are discussing how can we statistically establish a difference. By the way, what is the inference we are getting right now? Inference is that car type is a significant predictor of mean pressure. And if I look at the ANOVA test once again to show you, you will see that the p-value is coming as 0.001. The p-value is actually less than 0.5%. 5%. Which again tells me that indeed car type is a significant predictor of mean pressure. And when you form that ANOVA table, that ANOVA function, please go back and put mean pressure as the output. Output will come on the left-hand side. This small swiggy sign will come up here and the input will come on the right-hand side. Okay, that is how you frame it. Slightly difficult stuff, but this is the kind of stuff you actually need, right? No point discussing easy stuff. This is how you actually use these things, right? How do you use it? This is how you actually use your t-test and ANOVA tests. So you use your t-test and ANOVA test to actually decide whether a feature is significant or not significant. It is basically called feature selection. Okay, and this is what we do as a precursor to machine learning, right? As a precursor to machine learning. So even before you start building your machine learning models, oftentimes these questions will be asked that, hey, what are your important features? One way you can answer the question is through your hypothesis. You will say, okay, just like we solved this question, right? You will have your hypothesis in mind that, okay, for doing the, basically for doing this particular case study, we saw that, okay, the most important predictors were, let's say we are forecasting food demand, right? Swiggy, tomorrow, how much will be the demand? So one way to answer the question will be the hypothesis you will have in mind, right? The hypothesis you will have in mind. Okay, these are the factors that will actually affect food demand. What kind of food it is, which locality you're from, will it be raining tomorrow? Okay. The other thing is statistical thing. Statistically, this is how you'll do it, right? P-value less than 5%, feature significant, else it's not. Okay. And then you will use only those features for your model building. Having said that, we straight away don't drop features, right? As we said for correlation, we straight away will not drop features. So what will we do? We will use better techniques, which you will probably learn later on down the line. It's called feature extraction and PCA. Right? So how can you, instead of saying, okay, feature 1 is not significant. So for example, here we said gym 1, right? So gym is not a good feature. If I just go back here, we said gym was not a good feature. So should we drop it? Well, I mean, there are several thought processes behind it. Well, probably we can drop it. But then the other way to do it is probably gym will have a good interaction effect with some other feature. It's called interaction term. Right? So what I'm touching upon something right now is called interaction term. Gym by itself may not be a good feature, but gym might have a good relationship with some other feature. Very interesting. It's called interaction term. And this part is a little advanced, which I don't want to get too much into right now. Just to give you a basic overview of this part, what I'm trying to touch upon is, let's say you have this example. let's say you have this example, location and discount of different, so you're basically looking at quality of service, quantity of items sold based on location and discount. Very interesting. This is supermarket data, transaction data, right? So location is basically, location 1, location 2, discount is how much discount you're offering, and quantity is how many items you're actually selling. Simple data frame, right? Quantity is a numerical variable, discount is a numerical variable. Actually, discount we can think of categorical. It's a discount bucket, and location is obviously categorical, right? So now what we are trying to decide is, we are trying to figure out that which are the important predictors of discount. Quantity. Quantity is my output, location, discount are my inputs. Feature selection, once again, straight away ANOVA test, right? Again, we are discussing how are we using ANOVA in this context. So what can we do? I'll straight away come back to the ANOVA table interpretation. And now if you see, very interesting, if you see the ANOVA table right now, discount has a very low p-value. Discount has a very low p-value. So look at the ANOVA interpretation quickly, all of you. So you can see that quantity is what we are trying to predict. And quantity we are trying to predict using discount, location, and an interaction term of discount and location. This is called an interaction term, right? So discount, location, interaction term. It's called an interaction term. And this is what I was talking about. It's a little advanced part, this part. Interaction means discount and location, they are themselves related. The features are themselves related. Okay. So it's called an interaction term. So now, if you see, very interesting, discount is a very good feature. Quite obvious, if you're having higher discounts, people will buy more. So discount and quantity are very highly correlated. And you can see the p-value is very low. So p-value is significant here. P-value is very less. That means discount is a very significant feature to predict quantity. But very interesting, location is not. Location is not. Location has a very small p-value, a very high p-value. By the way, what is e power minus 1? E power minus 1 means 10 to the power minus 1. E basically stands for 10. So 5.06 into e power minus 1 means 10 power minus 1. Location is not a good feature. Doesn't matter, right? Maybe your location 1 and location 2 are both metro cities. So whether it is Bangalore or Mumbai, the outlets are in Bangalore, Mumbai, both are metro cities. What does it matter? Doesn't matter, right? So location turns out is not a good predictor of sales. Bangalore Reliance Retail will also sell high, and Mumbai Reliance Retail will also sell high. So turns out location by itself is not a good predictor. But very interesting, when I combine location and discount together, that becomes a good p-value. It is still higher than 0.05, but it's still better than what I had before. Right? So very interesting. This is called an interaction term. Be aware of it, all of you. This is how you actually use ANOVA test in the context of feature selection. Right? All right. Now, finally, so this kind of fills up this bucket. So this kind of fills up this bucket of, so now we know numerical, you have correlation, you can use your correlation. But then having said that, the theoretical surface we learned, okay, if correlation is less than 70.7.6, drop the variable. Please don't do that, okay? Leave it to the machine. There are more advanced techniques like feature selection through which we actually do things, right? So don't say we'll simply drop the feature. We don't do it, right? Good to learn, but then we don't do things. We don't drop features like that. And then numerical, categorical, or categorical, numerical, we actually go for ANOVA test. There are other feature selection techniques also we have. Probably some of those things you will come across once you do machine learning. But what I'm trying to get at is up to what you have learned so far, just to help you connect the dots. That's what I'm trying to focus on. But there are obviously much more deeper aspects in this that we can actually do. Feature selection by itself is a massive topic. Actually, there are libraries in Python you can use. There is forward selection, backward elimination. There are lots of different ways you do it. But this is purely from a statistical and EDA perspective, how you do the initial feature selection. Even before you start your data science problem, how do you have the hypothesis? Okay, you know what? Food demand. I think food demand can be affected by whether it will rain tomorrow. Maybe that's a hypothesis you have in mind. Using ANOVA, you're only trying to test your hypothesis. Okay, how strong is my hypothesis? You're only trying to test your hypothesis. Okay, if I launch the VR device, how high my new mean will be. It is just purely from a very initial, hypothesis perspective. You're basically doing these tests, right? And finally, what about categorical? Categorical, that will be chi-square test. And again, I'll just show you the implementation of chi-square test. Categorical could mean your, let's say, Titanic dataset. What kind of datasets have you worked on? Just for my understanding. Okay, maybe let's say, okay, just for my understanding, what kind of datasets have you worked on? Any example you can take. We can relate to it. Titanic, have you seen? Have you all seen Titanic dataset? Probably you've seen Titanic. Okay. Okay. No, Titanic you have not seen. All right. You would have seen Titanic, right? All right. Okay. Some have seen, some have not seen. All right. So that's okay. No problem. I'll not make any assumptions. All right. No, Karthik, you have not seen. No problem. Okay. So let's kind of focus on what you have seen today. Let's focus on what we have seen today. What have we seen today? Today we have seen the country's data set, right? So can we establish a relationship between something between country and continent? Country and continent. It's a very simple problem statement I'm taking. Or let's say we'll go back to the, we'll go back to this one. Let me open up the case study once again. Let's say we go back to the loan prediction problem. Can we find out a relationship between graduate versus gender? Okay. Or let's say, can we find out any relationship between, just quickly open it up. I'll just browse the chi-square. I think I'm running a little out of time, but I'll take 5 more minutes of your time. Okay. Yes. Okay. All right. Okay. So can we find a relationship between married versus, I don't know, married versus what? Maybe, or maybe education versus property area. That could be very interesting, right? That could be very interesting. We've got two categorical variables, maybe education versus property area. Now, there's not to have any bias or anything of that, but maybe if you're from an urban area, maybe property area urban means maybe the probability of being educated is high. Maybe your chances of being a graduate is high. Maybe, I mean, just not in today's world probably, but still you may have some relationship, right? So education versus property area. Do I have a relationship? Can I really say there's a relationship between the two columns? Right? So these are the kind of things that you can establish with the chi-square test. Right? Look at any two categorical variables. Okay, do I have a relationship between gender and married? Okay, do I have a relationship between married and graduate? Maybe married and education. Very interesting, right? Okay, so, and people who have done Titanic probably, do I have a relationship between gender and class? Or do I have a relationship between gender and survived? And actually, if you go back to Titanic data set, you will see that females actually survived. Or maybe class and survived status. Right? So people in first class cabins actually survived, right? So maybe they're rich people, right? Rich people from a higher class, female gender, young children actually had very high chance of survival. So the significance level is very high there. How do you do this in a real-time scenario? We'll look at a simple problem, okay? We'll look at a simple problem. And what we are seeing here right now, we are having a data set like this, gender and perfect, satisfactory, defective. So this is how we actually do a chi-square test. And again, you can have these as two separate columns. And what you simply do is you get a statistic here. Same way, you look at the p-value. What is the p-value? If the p-value is less than 5%, you will say there is a relationship. Okay? You will say there is a relationship. Okay? And what is the problem statement we are looking at right now? Here, we are looking at gender and the kind of products they are manufacturing. Are they manufacturing perfect products, satisfactory products, or defective products? Gender versus the type of products they're manufacturing. Is it perfect? Is it satisfactory? Is it defective? Right? So, I mean, so chi-square test, with a chi-square test, we can actually establish a relationship. Again, the implementation details are not so important here. The concepts of hypothesis is absolutely, you need to have, but beyond the point, as I said, once you start getting into machine learning, these concepts, statistical analysis as we know it, from a very classical stats point of view, will not be very relevant. But how do you use these principles in a real-time data set? Like, for example, to look at feature selection, that perspective is still very relevant. And to give you another example of it, let's say you're building two different models, right? Model 1, model 2. You've probably used linear regression, and you've used a slightly more advanced model like support vector regression or a bagging regressor. And now you have two different model accuracies. Now you are trying to decide that, hey, which model is better? Model 1, okay, I'll give a simple example to you, how to actually use it. Again, in a real-time scenario. Okay, so model 1 is giving you 80% accuracy, and model 2 is giving you 85% accuracy, right? So which model is giving you higher accuracy? So naturally, model 2 is giving you higher accuracy. Now the question you need to ask yourself is, when I go from model 1 to model 2, is the increase significant? So the question you're simply asking in all of hypothesis testing, it's a very, very a confusing topic typically, and it's very theoretical. Usually you learn a lot of theory here, right? But now a simple way to understand this is the increase significant? Right? Is the increase significant? So when I go from model 1 to model 2, if I try with a different model, the increase of accuracy I'm getting, is it significant enough for me to actually go to model 2? Is it worth investing on model 2? That's the kind of question you're actually asking. And again, these are all beautiful examples of t-tests and ANOVA. Okay, you can straight away look at p-values. None of the mathematics is relevant from this point onwards. You can straight away do your t-tests, one line piece of code in Python, t-test ind and t-test one-sam t-test function you can use, right? And look at your p-value. If p is less than 5%, feature is significant, right? That's the simple takeaway you should have from all of stats, right? So please learn how to use these things in the real world, right? So how do you actually use your t-test? How do you really use your ANOVA? How do you really use your hypothesis in the context of machine learning? But having said that, classical statistics, as I said, will not be very relevant going forward after this point. But the other aspect of statistics, the summary stats part of it, the descriptive part, stats part of it is very relevant. So please be very, very comfortable in that part. So there should be absolutely no doubts on that part. So when you get a data set, you should be comfortable with finding out your missing values, your outliers, your EDA, the different types of plots, because that is very, very important, because that actually helps you understand what your driving factors actually are. Right? For example, if I'm doing the food demand forecasting, if I have to forecast that, hey, how much, basically, if you think of from Swiggy's point of view, it's a very hard problem, right? If you think of Amazon's point of view, for Amazon to forecast that, hey, how much of inventory should we keep in this warehouse for tomorrow? It's a very hard problem, right? It's a very hard problem. And to do that, you have to know what your drivers actually are. What are your driving factors? Right? So obviously these are some very obvious driving factors. We need to know number of orders, location, price, food type. These are obvious driving factors, right? But then the idea is, okay, am I sure of these driving factors? This is what I think are my driving factors. Okay, but am I sure? Can I validate it from my past data? That is where EDA comes in. EDA comes in to help you validate whatever hypothesis you have in your mind. You think whether it's a driving factor, but is it really? Is it really? I mean, let me compare the days that have rained versus days that are not rained. Let me find out some inferences there. And now you go back and do your plots. You go back and do EDA, and you basically all through the process you try to basically kind of just validate your hypothesis. Very interesting. Base price and checkout price. You'll be actually amazed by this particular visualization. And this is again something that's not relevant for the session. So base price and checkout price. Typically, you will see that checkout price is always less than base price. Very interesting. I mean, it's obvious, no? I mean, typically checkout price, if you see, yes, in many cases it's equal or greater. Very rarely it's greater, but mostly checkout price is lesser. And almost always in Zomato, you'll find nowadays there's discount, right? 30% discount, 20% discount. So base price will be very high. Checkout price will typically be always lesser. Very interesting analysis we're actually seeing here. So we have some hypothesis, and now what we are seeing is, okay, how do we prove the hypothesis? I mean, are we actually correct? That is where EDA actually comes in. And very interesting. Okay, we maybe have a hypothesis that, okay, beverages sells more. And look at the EDA that we did here. Beverages clearly is a winner. When I'm analyzing this data right now, I can clearly see beverages is the winner. Okay, so this is the kind of stuff where EDA actually comes in, and EDA helps you approach the machine learning problem by figuring out, okay, these are my important features, and now we are just more ready to build our models, right? So, so I think the idea should be clear to all of you how we actually approach this from a data science life cycle point of view. I will not get too much into the life cycle bits right now because you'll probably be aware of it, and it's a little early to talk about it. But remember, this is how it typically goes about, right? You probably would have seen this before. So we look at our data, we get our data, we explore our data. The EDA part actually happens here, right? And this is where your model building happens. This is where your model evaluation happens. It's not enough to build a model. It's important to evaluate a model. The model comparison, the boosting the model means you're trying to improve the performance of your machine learning model. And finally, you're ready to deploy your models to production, right? So whatever you've done until this point is defining the problem statement, data discovery, data ingestion to get your data, data wrangling, pre-processing, how do you remove your missing values, how do you remove outliers, right? And EDA. This is basically all the stuff you probably would have completed until now as part of your program, right? Whatever you're going to be starting off will be from 0.5 onwards. Okay, so I think with that, I'll probably take some time on questions if you have any, and I think we are a little out of time. It's a bit of a deep topic, but any questions I'm happy to take up. Yeah. All right, any questions, you can just shoot and we'll take up some other questions for all of you. Yeah. Anything at all? I mean, generic questions if you want to know something about machine learning, and feel free. I mean, there's no such limit on what kind of questions you can ask. It's just be generic, and anything at all you want to ask, just shoot. I mean, anything about you want to know, anything at all. Yeah. Some of these dots might be a little hard to connect, as I said. Once again, I mean, as I say, statistics otherwise is a pretty dry topic, but you should understand where it is actually used, okay? Where it is actually used, how it is used. But having said that, many of these things, especially the inferential side of things, hypothesis testing, will not be very relevant once you go to machine learning. It will be very limited, coverage you will actually find. But EDA, you should be absolutely good. How important is boosting? Well, boosting is very important. I mean, obviously, there are some very popular algorithms out there, gradient boosting and XGBoost, very popular algorithms. And Ganendra, since you know the domain a little bit, boosting is primarily used to reduce your bias errors, right? How do you reduce the bias errors of your model? Bagging will be used to reduce variance errors, and you can actually use. So, for example, I'll give an example to you. Try using boosted random forests. Right, random forest will reduce your variance errors, and if you use boosted random forest, on top of reducing variance errors, you can also reduce the bias errors. It's a pretty powerful model actually. Okay, XG boosted random forest. So boosting is pretty important, obviously. I think you'll learn it much later in your curriculum. It's an ensemble technique. Ensemble means how you combine multiple models together into one single model. It's an ensemble method, right? And probably it will come a little later in your program, mostly. Yes. Cool. Anything else, guys? Hope you were able to connect the dots, where the pieces come in, what are the pieces. Yeah, that part is important, right? Otherwise, theory you can all understand, but be aware of how these things are actually used in reality. Yeah. And always start thinking from a case study point of view, right? See, interview questions, I look at it slightly differently. What I would say is, please don't, okay, see, the way I would like to put it is, if you go to Google, just search for top 50 interview questions, you will find hundreds of it. But trust me on one thing, if you're going for good companies and good interviews, nobody will ask you questions like that. People will not ask you questions, the kind of stuff that they put out there. What is hypothesis testing? What is t-testing? What is p-value? Nobody will ask you bullshit like that. Okay, so that is the kind of stuff that that is posted. Top 50 interview questions. Some joker will go on YouTube and they'll record a video, top 50 interview questions. That is not how it is done. I can assure you of that. Maybe initial phone calls, telephonic interviews, first 5 minutes, first 7 minutes, they will ask you those kind of basic questions, right? But the idea is, please don't get into the mindset that in something as deep as EDA and people will not ask you what is a histogram in a theoretical way, right? No, it doesn't get asked that way, right? So be very, very comfortable with the content that is covered to you, and you don't even have to worry about interview questions, which is why when I take up these sessions, I don't, otherwise it will be like, question one, interview question one, this, interview question to this. Good companies will never ask you questions like that, right? It will always be case study based. It will always be data set based. Remember, in data science, data is a driver of everything, right? Unlike in traditional statistics, where question is a driver. So we'll give you a data set and we'll tell you, hey, please tell me what you can find from this. That is how all data science interviews actually go. A data set is given to you, and now you're asked, okay, this is what I want to do. Now on this, you do your EDA, you remove your missing values, outliers, everything you do. You tell me how to handle this data. And that is how it always flows. It is always case study based. It is not based on interview question in one, those are all basic questions, you'll find it, right? And in those questions are like what? Like, they'll ask you, okay, what is the p-value? What is the t-test, right? What is the difference between z-test and t-test? You already know these things, right? Sigma is unknown, right? These are all basic things. What is standard deviation? And what is standard deviation? Okay, what is high outlier? These are all obvious stuff, right? So if you're okay with the concepts, if you're okay with the case study based approach we saw today, then I think you should have no difficulty with the interviews, right? So please don't be so worried about. Otherwise, you'll have hundreds of blogs where you can go. Analytics Vidya, they'll publish top 70 interview questions, and actually many of the time, interviewers themselves will go and ask from there, because many of the time they will also not be very knowledgeable. Okay, that also happens, right? All right. So getting confused between critical method and p-value method. Okay, so there are two ways of doing the same thing, Khushbu. That's a good question. If both are for the same purpose, which one should you follow? Again, like, anyone you can follow. They mean the same thing. Khushbu, they mean the same thing. If your X bar lies in the critical region, that means your p-value will be less than 5%, right? It doesn't matter. It doesn't matter which one you follow. Okay, and that's a good question you raise. If you go to some of the interview forums, again, all these very popular interview forums, they will actually ask you this kind of question. They'll actually ask you, okay, how should you find out this critical value of p-value method? And I just keep I don't know whether to laugh or smile when I actually come across that interview question. Actually, this gets asked an interview question. The idea is the same thing. When you start drawing, when these kind of questions are asked, I will recommend don't answer it that way. Please draw a figure, draw that normal distribution, show them the critical region. This is the critical region. If my X bar lies in the critical region, that means my p-value is less than alpha. Done. That's it. In less than 30 seconds, you have answered your question visually. right? So both are absolutely the same ways of solving the same question, right? Yes. And alpha you can actually define. It depends. I mean, alpha is something that will be, as I told you already in the beginning of my session, alpha is something that will be dependent on several parameters. Oftentimes it is decided by the business, right? So you don't, in reality, you don't do alpha for 5%. I mean, 5% is the default, but in reality, we conduct hypothesis tests for several different values of alpha. We'll do hypothesis tests with alpha equal to 5%, 1%, 0.1%, 0.01%. And usually the test results will be given at several different significance levels. And now it is left to the management to decide what level of error they are willing to tolerate, right? So because alpha is the level of error, right? So now it is up to the management that, hey, what level of error are you willing to tolerate? That is not a statistics question, that's a business question now. So in reality, when you do hypothesis tests, you will do it at several different values of alpha. Having said that, from a machine learning perspective, it's a very different ballgame. As I told you, inferential stats, as you learned it, you will not be using it that way here, okay? So just be clear on those distinctions, all of you. Yes. Okay. Others, any questions, guys? Just shoot anything at all, generic questions you want. Otherwise, I think we can wrap it up. Yeah. Hope all of you are able to follow the initial part. Initial part is important. Again, as I said, it's not so relevant from an ML perspective, but it's very important that you get a hands-on idea of solving hypothesis testing questions. It's a little boring, but you should not know it, right? So because in good tough interviews where they ask you, core stats concepts, some of these questions can actually come up, right? So be very, very comfortable with solving your, the hypothesis testing questions with a pen and paper approach. So Python is important, but this kind of pen and paper approach is also very important because ultimately it's all concepts. So we can forgive you if you don't know Python. So for example, like the kind of stuff I was doing, right? Pretty comfortable with typing out a few commands, codes. That's okay. I mean, even if you don't know this, even if you don't know syntax, we can forgive you. But concepts you should be absolutely clear on, right? So okay, if you do a box plot, you can at least draw it out for me. I'm still fine with that. But then you can't say I don't know box plot, right? I don't know box plot. That you can't say. You should know. Okay, categorical numerical comparison bivariate box plot is what I should go for, right? That much I'm expecting from you. I don't need to understand the code. That's okay. I can probably say, okay, Google it out. That's fine with me. All right. But you should not, concept should be absolutely clear. Don't be too intimidated with the code. That's another piece of advice I'll probably give you, especially for people coming from a non-programming background. Please don't be intimidated about code. Machine learning is not about coding. Machine learning is a domain where some of the top companies in the world, when they hire, they hire people from different domains. If you go to Facebook, for example, the kind of people they hired, there are biologists working in the team, right? They're biologists, they're people from mechanical background, they're working. So there are different types of people that are working, right? So, and especially in today's world, data science, machine learning, the kind of popularity that AI is enjoying today, and you can relate it to your own cohort right now. I think there are people from so many different backgrounds, right? So background is not a problem, and machine learning is not about coding. So please be very clear on that. It is not about coding. Coding and tools and applications are becoming more and more simple. And I think one amazing area that is really picking up in a big way is what we call auto ML. You can read about it. Very interesting field. Yeah. So I think it's a very interesting field, auto machine learning, where we are saying that, hey, you don't need to write a single line of code, right? So you just feed in a data set, put it in, something happens. The biryani is cooked and given to you in a platter. That's it. You don't have to add the ingredients. You don't have to monitor how the biryani is cooked. Nothing. You just put the ingredients, put it in a cooker, and that's it, done. And the food comes out for you. That's what auto machine learning actually is. There's a wonderful blog that you can read about it. And I always recommend Towards Data Science. It's one of the best blogs, one of my favorite blogs, one of the most popular blogs in the world of data science as we know it. It's basically a platform where a lot of, it's like a blogging site where you can come, a lot of popular authors blog here. It's a very nice article, you can read about it. And there are some very popular tools in this space, which are really taking the overall, auto ML landscape by storm. You can read about it. Data Robot is one such tool. Automated machine learning, how amazing it is. Put an Excel file, put it in, something happens, and the predictions come out. Okay, so I won't be surprised if for the next 2-3 years there won't be any Python anymore, right? So you don't have to do Python anymore, probably. and having said that, there are already platforms. For example, if I show you Nime is a very popular platform. If I just have to show you, look at this. So this is basically a machine learning model that we have built in Nime. What have we done? Taken an Excel file, drag and drop an Excel reader, color manager, statistics, double click on it, mean, median, mode, we can set whatever parameters you want to set, all drag and drop, just like Excel. No coding involved. It's a decision tree is basically a machine learning algorithm. Again, no coding involved. Okay. The idea that I want to enforce here is get your concepts right. Programming is not important. Okay. Programming is important from an implementation standpoint. Yes. But then it might happen that by the time you get into your roles, your jobs, it might happen that your organization is probably implementing in a different tool, which is very much possible. There's so many different tools out there today. Okay. More and more tools are coming up, which are making development easy. And from a business management point of view, if I'm the project manager, naturally, I'll prefer a tool which is easier to implement, right? So having said that, Python is easy. It's not difficult, but be open-minded and don't think of this as a Python course. It's not. I mean, be comfortable with it, but it's not the end of the road. Okay. But absolutely be very, very clear with the concepts. All right. So we are moving towards course concepts are, okay, I think I pretty much answered that, Jignesh. That makes sense. I think I pretty much answered that question for you, I believe, yes. So how much confidence should be with syntax? As I said, typically when some of these open interviews are conducted, yes, I think syntax is something that you can be forgiven for that. So please don't worry about that. Most of the time, Google is available. Hackathons, if you participated in one before, typically some of these open hackathons that are conducted, and lot of companies, lot of organizations, and even upGrad, we organize some of the hackathons. I think recently we tied up with a few companies. There were some open hackathons we conducted. So in many of these hackathons, Google is open. So there's nothing to memorize. The code is not to be memorized. But having said that, you cannot say, Sayan, I forgot how to read a pandas data frame. See, there is no excuse for doing that, right? Read CSV is something you should know, right? There's no excuse for saying I've forgotten how to read a CSV file. That basic concept you should understand. And that will come with practice, right? So obviously, that will come with practice. But if you say, okay, I forgot how to, let's say, how to sort in a list, that's fine. I mean, I know what is an np.append, I know what is a list.append, but then I forgot how to sort it. The dot sort function, I want to just quickly look it up. Go to Google and pick it up. That's fine. It's just Stack Overflow, just copy paste one line of code. You have to be very, very good in copy paste here, right? Be very, very good in copy paste, but you have to be very sharp to know what to copy paste, right? So that's the idea. A good in aptitude you need to be in this domain, right? Yeah.